Hello, hello. How's it going?
All good.
Amazing. So this is like time of the year when we're meeting at TensorFlow conference, or?
Usually, yeah. Before COVID.
Yeah. Like I remember back in the days, it's gonna be like this, like a big, almost like a party of people going from all the locations, right? But today we're still in different locations, but just like in different geographies, right? Like where are you guys right now?
Oleksandr, you want to go first?
Yeah, I'm in Krakow, Poland. And you, Alejandro?
I'm in Copenhagen, or west of Copenhagen in Vallensbæk, for who knows where that is. Yeah.
Cool. Sergii, and where are you?
Yeah, I'm in Munich, kind of close to the Alps, and the weather today is also like very Alpy, right? So there's like a snow was going through. So it's good to have some combination of staying home, but it's also nice to meet you people, at least like online as well.
Yeah, definitely.
So, what do we have on the agenda today? Should we start with just a quick update on the different TensorFlow user group, maybe from our side?
Yeah, definitely. You can go ahead.
Sure. Yeah, so good to virtually see you all. And I really hope there are many joining from the Copenhagen TensorFlow user group. As some of you probably know, we started the TensorFlow user group February 2020. We were arranging an event to start on March 14th. And the Prime Minister come out, I think, the March 11th, and communicated we're closing down the country, and we had to cancel everything. So we have not actually been able to do anything live meeting until now. All have been virtual, just like this one. But I'm really hopeful that we soon can meet together. We have at least the Google office for the first meeting, and then we will see where else we can meet. But what I really would like to ask for the community members, if you just can share in the meetup group, what are your interests? What are you interested to listen at? How you would like to engage with the meetup? The more active we are all, the better for everybody. So look forward to see your comments on the meetup group. Thanks.
Nice. It's like hell of a story, right? When the prime minister is like a part of a meetup community, right? I wonder if he's actually, or she, they're actually watching the same stream, right? Because maybe like, hey, it didn't work out with the real life, right? Maybe at least like online.
You never know.
How was it for you, Sashko? How is your community going?
Well, my community, I hope we will renew operations this year. We've organized an event or two just before all these COVID-related closures were announced, and frankly, we did not really succeed to find the best format suitable for online events. So we went into a hibernation mode. But now with the TensorFlow everywhere, I think we will operation. So yeah, hey guys, whoever is calling in from Krakow, good to be with you.
I do think we have some technical issues. Is it just me they're hearing? Or just me, probably? Sorry for that.
I think it's fine so far. Yeah, if anybody hearing any issues, please comment on YouTube as well, so we can see what's happening.
It's my newbie with StreamYards and YouTube channel, so I'm playing both. So I hear the echo from YouTube. Sorry for that, for interrupting.
No worries, completely fine. Yeah, so Krakow is definitely like a lovely city. Been there once or twice, yeah. Yeah, for Munich, it's basically very similar. We tried a bit of like recording even pre-COVID time. And after when all of this like craziness like went into, I was actually experimenting like with a few like online events. So we didn't really like went completely like offline. We had a few events like every now and then, but it's definitely not so easy as with like online events, sorry, with like offline events, right? Because with offline or on-site events, right, it's easy to get, attention of the people like all in the same room, right? And everybody's like, really in the place, right? Really paying attention to what's happening. And with online, it's just like another tab or in your browser, right? And it's like really hard to compete, basically. But I do hope that today, with such amazing speakers that we are having, it's not going to be like really complicated to compete, right? Because we really have like top of the top, right, and really exciting speakers to have. What do you think like the most exciting that you're going to learn today? Like, what is your expectations?
That's a tough one. I look forward to all three. TinyML is definitely interesting. On the other side, on my normal job, what Gus is going to show is super powerful, especially for the Danish market, where we have super strong focus on audio. We have many of the biggest companies in the world that are building hearing for people with hearing difficulties. So I think it'd be interesting. MLOps is definitely also a topic that are super hot at the moment.
Yeah, that's a very good opening to the next slide. So I definitely agree with you that TinyML, I mean, it sounds like tiny, right? But as Pete said, like in one of his tweets, right, that the future of ML is tiny, and I definitely see like a lot of opportunities, right? But there is also like almost every topic that we see on the agenda, right, from making our machine learning like modular, right, to making them like into production. There's like so many really like on the agenda topics, right, that each of our machine learning engineers today needs them, right, and would definitely have like a good benefit. What do you think, Oleksandr, your favorite topic?
Well, all the three of them. I think all the three of them are the ones that are modifying the whole industry now, right? TinyML, the ability to run models on small devices, on microcontrollers, and TensorFlow Hub as a repository for the models. I mean, the small startups that never dreamt of being able to use machine learning can now take the model off the shelf and turn it into a useful feature. And obviously, all the topics that Hannah covers in his book, and I hope it will also be in his talk about building machine learning pipelines. It is essential, right? It is one thing to do this stuff in academia. It is much, much harder to do the same stuff in production. So looking forward to all of them.
Yeah, definitely. So basically, for those of you who already heard like what's happening, right, you can also see that we have like 3 main talks, right, and in between them there is like a tiny breaks, because we all still humans, right, and maybe you wanna grab like your tiny fast dinner or just like water or whatever is like working for you. And after that, we're going to have like lightning talks, right? Lightning talks, it sounds that it's something like smaller, right? Because they actually going to take like only 15 minutes, but information density there is going to be like way higher, right? So people going to be like really feed this great use cases and great like learnings into this time limited horizon there. Like there's one from Brainly, right? There is like one from like ZenML about reproducible machine learning. So definitely looking forward to hear like all of those things that speaker is going to bring us today.
Yeah, and at the end, we will be giving out books, right? Worth mentioning.
Yay!
Yeah, we have gifts.
A tiny surprise from 3 machine learning communities. How does it work, guys? Like who's going to get the book?
So we have the fortune to have speakers that also have been author of books. So we thought it was the most compelling thing was to give away a book where you could deep dive into the topics that they're talking about. So how is it going to work? Good question. Alexander, you have the details there?
Yeah, the people from the audience who asked, or who will ask rather at this point in time, who will ask the best questions will get the books. So yeah, we will announce the winners at the very end of the event. So stay tuned.
Yeah, so pay attention to the talks, right? We're going to select like the most exciting questions, obviously. I mean, we're not going to be making any decisions here. The speakers, right? And at the end, as Sashko already said, right, we're going to bring your names on the slide and figure out how to send those books to you. So really looking forward what you're going to ask and what speaker is going to present. And with that, I guess we're going to start with the first talk, right? Or how do you feel, guys? Do you have anything else to tell before we begin?
Yeah, enough waiting. Let's go ahead.
Yeah,
with the talk.
let's go ahead.
All right. Guys, I'd like to introduce Pete Warden. He's a research engineer at Google and is a co-author of a really great book on TinyML. I think, Pete, you also wrote 2 books on machine learning back in 2011, I think.
Yeah, don't buy them though, they're so old now.
Yeah, and also Pete is an instructor and an author in an EDX course on TinyML, which I really highly recommend. So Pete, it's all yours. Take the seat.
Awesome. Thank you so much. I'm just going to share my screen. And I just also put a link to the slides in the chat. So if anybody's able to, share that in the description, that would be great.
Yeah, I will repost them in the chat on YouTube.
Perfect. Thank you so much. So yeah, hi everybody. Hopefully you can see my screen. So because I have a lot of URLs in my talk, I'm not going to expect you to scribble them all down. So if you see this short URL, you can use that to actually get to a public version of the slides and find all of the URLs that are on here. So with that, I'm Pete Warden. I'm the tech lead on TensorFlow Lite Micro at Google. And the reason I'm here is because TinyML is a really exciting subject to me. And I actually have some funny connections with all 3 locations of the user groups. Some of the software that I'm actually going to be showing from Ant Micro is produced in Poland. I've actually spent a lot of time with especially auto car manufacturers in Munich who are looking at putting embedded machine learning inside the kinds of embedded devices that you get as parts of cars. And Denmark seems to be a real hotbed, especially around audio and hearing aid devices. So I think that's going to tie into one of the later talks too. But what I'm here to talk about is how you can actually take machine learning, this thing that you often think of as being a very cloud-based, something that you run on big GPUs, on TPUs in the data center, and actually bring it down onto much, much smaller, cheaper devices. Things like Arduinos, things like Raspberry Pi Picos that just came out, things like ESP32s. And all of these devices are very different than the computers that you might be used to, because first, they're super cheap. ESP32s, you can pay just a few dollars. Some of the devices that we run on, you can actually buy for under $1. Now, they don't have much in the way of resources. They might only have tens of kilobytes of memory. So it's pretty challenging to get things running on there. But in return, you get something that is really small, really cheap, and that you can potentially run on a battery for weeks, months, or even years. And that's something I'm going to be returning to, is the idea that you can have these devices that are very, very self-sufficient, that can kind of live out in the world without having to be plugged into the mains, without having to be recharged every night, without having to have batteries changed. Because it might seem like a small thing, but taking that element of human labor out of the devices opens up all of these possibilities for having them all around us in the world. And the project I'm going to be talking about, TensorFlow Lite Micro, funnily enough, its original code name back when it was a research moonshot was actually TensorFlow everywhere, just like this series of talks, because the idea was that we really wanted to see, hey, how can we get TensorFlow out from the cloud and desktop machines and phones and actually get it running in the wider world all around us. And you might be wondering what sort of things you can do with it. There are lots of different flavors of things you can do with machine learning on these small devices, mostly because they actually have a lot of sensor data coming in. The nice thing about working on these is that they have all of these different microphones, accelerometers. You can attach very small, low-power cameras, and that means that you're actually able to do things like simple speech recognition. I'm going to give you a demo of gesture recognition, and you can even do things like computer vision, and that still kind of, you know, gets me excited and kind of blows my mind that even in just, you know, tens or hundreds of kilobytes of memory, you can actually do these very advanced things with machine learning. And in this talk, I'm going to be trying to focus on giving you some actual demos. So I hope you'll actually bear with me and wish me luck, and hope that the demo gods smile on me, because I'm going to be showing you some stuff that I'm running off the fly on my machine. And just to get more concrete, when you think about the sorts of things that favorite recent examples that I ran across, on Twitter, I think it was, where somebody had taken the TensorFlow Lite micro framework that I work on for running machine learning on these tiny devices, and they'd actually got it running on an ESP32 that just costs just a few dollars. And what this is doing is it's taking the display of an old school analog water meter and running machine learning to actually recognize the dials and the digit displays on this device. So just by pointing this really low power, battery powered device with a camera at a water meter, it turns it into a connected device. So this is pretty exciting to me because it's a very clever solution to a very tricky problem. You have this world full of infrastructure, and infrastructure, things like water meters, things like oil refineries, things like agricultural equipment, they don't tend to get replaced very often. They might only get replaced every 40 or 50 years. And it's because it's very expensive to actually replace something that's working with something newer that maybe has newer technology. Because if you think about like a water meter, if you actually want to replace it, you're going to have somebody who's got some kind of plumbing skills go in there, turn off the water, put in something new, figure out how to get power to it, attach it to the mains power somehow. And that's a lot of work, and it's not likely to happen very often. But it's really useful to be able to have access to information about, how much water am I using? What are my water usage patterns? Try and get all of that smart information from a water meter. So by taking this really cheap an easy solution, I sometimes talk about peel and stick sensors, where you can take a device that's battery powered and just kind of stick it somewhere. And in this case, stick it so that it's pointing at the water meter. And it's actually able to read all of the information without having to go through all of that extra work and that trouble and that hassle of replacing the entire system, and adding completely new hardware. I think this is really clever. And I also, when I tweeted about this, I heard from a bunch of other people who are doing similar things. For example, taking things like soil humidity meters and that have displays on them but that aren't connected, and actually using a technique like this of doing, if you've ever done AI ML tutorials, you'll know that MNIST, recognizing digits, is one of the first applications you do. Just by doing something very similar to that, you can actually turn all of these things with these digit displays into IoT connected devices very quickly and very cheaply. So this is one really interesting application that I wanted to show off, just because it kind of really struck me that it was something that I'm expecting to see popping up in a lot of places over the next few years. And it might not be the sort of thing that you think of when you think about machine learning. And this is another use case that I really enjoyed, that actually just popped up in the last week. And it's actually using Edge Impulse, which is a great company that you should check out, a startup that actually adds a whole lot of value on top of the TensorFlow Lite Micro framework by giving you kind of an end-to-end solution for training online as a service. But one of the things they've actually helped enable here is taking this really low resolution infrared camera and actually having it detect when there's a person visible in the camera or not. And this is something that somebody just put together pretty quickly and pretty easily with a bunch of off-the-shelf devices. And this is something that a few years ago would have been very, very hard to do if you could do it at all. And now we're opening up this whole world of prototyping and allowing people to create these solutions where they might have struggled before. So this is the point where I take my life in my hands, and I'm going to attempt to do a live demo of some of the things that you can do with TensorFlow Lite Micro. And this is actually a demo from the edX course that I'll link to later, using TensorFlow Lite Micro. And what I'm going to be doing is showing you how you can actually use an Arduino BLE, and I don't know if you can see this, but I've taped it to this magic wand. And what I'm going to be doing is showing you how you can actually use the accelerator, the accelerometer and the IMU on this to take in raw accelerometer data and then figure out what gestures you're actually doing with the magic wand. So you can actually turn your Arduino into a magic wand, which through Bluetooth you can actually, imagine triggering all sorts of interesting things. So I'm going to just make sure that everything is running correctly. Let me see if I can connect. So I've just used WebBLE to connect to the Arduino, and I'm going to try doing a gesture. So you can see there I did kind of a 7, not a very good one. It thinks it found a 2. So let me see if I can try that again. Okay, that's better. It definitely thought that that was a 7. Let me see if I can do a 6. And you can see in the Arduino output here, it actually found a 6 using the ML model that I've trained to recognize digits. And the nice thing about this is that this web page also functions as a way of capturing data. So if you want to train your own gestures, the edX course will actually show you how you can go through and actually create your own gestures. At the moment, I've got it recognizing digits, but you can have it recognize anything you want. I quite like doing sort of a nice Zorro Z. That's pretty satisfying. So since that actually worked, I'm going to, get back to some slides, and then I'm actually going to go back to giving you some more demos. And I'm going to be showing you some Python, since that's an important part of what we're talking about here. But I want to take a moment just to come back to some of the really important use cases where this kind of technology can help. One I actually didn't put on here, but that I'm reminded of from the Copenhagen connection, is actually helping people with hearing aids. There's some amazing work that's been done actually pulling out an individual voice from a noisy room. And if you think about being able to run that in real time on a tiny battery-powered device in your ear, imagine how much that can help somebody who's struggling with hearing loss. And I'm expecting to see some really fantastic applications starting to come out. We already see published research that shows really good results. They should be making their way into the real world, into production soon. Now, another place where I've seen a lot of really interesting work happening is around agriculture, around helping us all grow food in a more ecologically friendly and efficient way by doing things like imagine having a small battery-powered device where they're cheap enough that you can just have them scattered throughout a crop field and actually spot diseases and pests visually. Just like we can look at a plant and tell, if we're trained, what diseases or what pests might be hitting it. If you can actually do that through a tiny machine learning model, that can help farmers actually deal with those problems in a much more specific way than just kind of spraying chemicals all over the field. You can actually have much more targeted interventions, and interventions that are better for the planet and also better for the farmers and better for us getting food. And in a similar vein, there's been some really interesting work happening in the wildlife community, especially around a lot of nonprofits, around things like tracking birds and animals, even through listening out for individual songs and doing recognition of not only species, bird species through their songs, but individual birds, which I think is really cool. So you can actually start to understand how many birds are in a location just by using audio. And one of my other fun use cases I've seen for this is actually doing facial recognition, but for bears. So using camera images of bears to actually tell which bear is which and understand the habits of bears as they sort of move around their environment without actually having to, do any kind of invasive tagging. Another use case that has come up is actually listening out for mosquitoes. I guess different species of mosquitoes actually emit that buzz at different frequencies. So you can do a lot of really interesting information around tracking mosquitoes. And then there's all sorts of personal health stuff that you can do. And again, if you're thinking about this, if you're thinking about this not being a phone app, but this being a kind of a peel and stick sensor or just a little device that you can sort of put on your clothing or something like that, that you don't even have to, think about charging, you can imagine how that can help, even with things like keeping track of your mobility, managing things like diabetes. One of my biggest problems when I was still in the office at Google was if you were stuck in a really boring meeting, the lights would go off because the lights would be triggered by movement in a room. I would love to replace that movement sensor with something that just does person detection, so that if there's somebody in there, it stays on. But if there's just something moving that's not a person, it doesn't stay on. So you can actually have much better building efficiency. And a story, like one of my use cases I actually ran across through a German engineering company when I was in Munich, was they were telling me that every factory has somebody that they called Hans, who every morning comes in and kind of puts his, and it's fairly old school, so it's often he, unfortunately, but puts his hand on the machinery and each piece of machinery and says, oh, you're going to have to take that offline today because it's running a bit funny. But Hans is almost always about to retire. So if you can replace Hans or help Hans out, give him extra help by having sensors on machinery that can actually predict when something is going to need maintenance, that starts to get really interesting. And that's even, all of these are kind of sensor-based use cases. There's a whole world of being able to run voice interfaces, speech recognition on any object. If you imagine being able to, over the next few years, hopefully we're going to get to the point where we can run a full voice interface on a 50-cent device that will run for a year on a battery. Anything that has a button or a switch is actually going to be added to with this kind of voice interface because it's going to be so cheap and so easy. So I want to give you some stuff that you can actually try out for yourself. So one of the things I want to show you is we have IPython notebooks, and we have them running through Google's Colab service. So if I switch out here, and just go over to the this IPython notebook. See if I can bring this up. Just a second. Let me see if for some reason my GitHub often seems to fail to render. Here we go. So if you look in the TensorFlow repo under TensorFlow Lite micro examples, you'll see a bunch of different examples for doing things like voice recognition, person detection, some magic wand examples like the one that I just showed you there. And if you look inside those folders and inside usually the train subfolder, you'll find that there's IPython notebooks for doing all of the training. So training all of these models, you can actually just do by opening them up in Google Colab. They'll have a link like this. Just click on that. It will take you to this link where the notebook is actually live. And if you follow through the notebook, you'll actually see that there's a series of cells together with a bunch of documentation for each step that kind of tells you about what it's actually doing. And this is the same material that's covered in my book, but you don't need the book to use this. Hopefully, this should generally make sense and talk you through. In this case, this is the hello world example, which is the simplest possible machine learning example we could think of for running on an embedded device. And what we do is we create a training set, which is a sine wave, and then we add a bit of noise to it so it's a bit more realistic as something that you might gather in the real world. And then we train a model using Keras and TensorFlow. And then we use that model. The first version doesn't work very well because it's too simple. But then we actually train a much larger model. And we actually come out with a model that looks a lot better. And you might be wondering, okay, this is nice, but what do you do with it? Normally, you would upload this to something like an Arduino and have it actually use the sine wave model to pulse the LED. One of the nice things that we actually have is some work that we sponsored from Ant Micro, who are based in Poland, which actually allows you to take the model that you've trained in the Hello World training, and you can actually use software emulation using the open source Renode framework to actually run that model on a emulated device. So if you go to, you'll find the links in the slides, and the slides are at this short URL if you need it. But if you go to the Ant Micro repo and look at TensorFlow Arduino examples, you can open these examples up in Google's Colab or anything else that you want to be able to run an IPython notebook in. You run this installation process, which installs and builds the Renode open source tool. And I'm actually going to run it live since it just takes a few seconds. you grab the script, and then you use the Python interface to the Renode emulation to actually emulate a Arduino Nano device on Linux. So you don't actually need a device to run this. So I'm just going to run this right now. And if you actually look at the output, if you plot this, these numbers actually form a sine wave that's being output from the TensorFlow Lite micro program that's running on the emulated Arduino Nano device. And you can do things like look at the executed instructions, look at the memory access, and do all kinds of really interesting debugging. So even if you don't have a device handy, you actually have the chance to do all sorts of really fun things just straight from Colab and Python. You can totally get started without needing any kind of devices. And the magic wand example that I showed you is just a small part of what you can actually find at the edX site for the Tiny Machine Learning course that's put on together with Harvard. It can be a bit confusing when you arrive there, because it starts putting up, prices like $500 or something like that. What you can do though is, as long as you don't want the certificate, you can just take the course and not worry about take it completely for free. Just register, and if you don't need the certificate, you can just go ahead and access all of the material and all the forums for free. I also have, if you prefer, or if you want to absorb some of this stuff through a book, I have this TinyML book that I work together with Dan on that covers a lot of these examples. And I would love to, get your feedback on this. And I've been talking quite a lot, so what I'm hoping is that you'll have some questions for me and some things that I can actually help answer, either right now, live on the discussion, or you can always drop me an email or contact me on Twitter if you actually want to do something offline, or if you have a longer question that won't quite fit in this format. So,
okay.
Yeah, that's it.
Super, Pete. That was super interesting, and thanks for taking the time, getting early up. Well, it's not that early because of the time zone shift, I'm assuming.
This was a good week to do it with the time change.
Exactly. So, Pete, I will take the liberty, as I'm the the host master here, to do the first question. But else, there have been some in the group. But I think it's a question worth for everybody. So you mentioned you could take this EDX course for free, and that's super grateful for everybody. Is there any need for any specific hardware for taking the course?
So another good European piece of technology, the Arduino Nano 33 BLE is the standard device that we we support a lot of different devices. We love them all. ESP32, a bunch of other STM32 devices, but if you're looking for a device to get started with, the Arduino Nano 33 BLE Sense is, I think, around $30 or $40, and you can even buy a TinyML kit that has a few extras like a camera shield and things for I think about $50.
Super interesting. So everybody save the money for the training and use that for buying the devices. So we have a first question from Lars, and he's asked, is it possible to train models on the embedded devices?
So that actually comes up fairly frequently. We do not offer full backprop. Like, we don't let you set up, you know, a model with variable weights and do training and things like that. And one of the reasons for that is that it's often very hard to actually have labeled training data in this embedded environment. So that has meant that there's, you know, we haven't run across that many use cases where people need it. Now, I'm sort of hesitating a bit because one way that we often see things being used is actually by doing simpler approaches to learning, doing something like taking an embedding out of a network and not changing the network itself, but using like nearest neighbor lookup on the embedding that you're getting out of the network to kind of customize and personalize results. For example, you could, like you do when you sort of set up a phone with like a wake word, you could say your version of a word and actually have the device, if you say it sort of 3 times, the device could learn what your embedding results are and then use that to help better recognize when you're saying, you know, OKG or whatever it is versus, you know, somebody else saying that. So that's a nice way of doing training without having to do, you know, or doing personalization without having to do full training.
Okay. Would it be relevant to say this is an open project for research, maybe, as it is an open source software? Anybody
Definitely.
in the community who are willing to engage in this kind of projects, maybe reach out to Pete and see how you can collaborate on that.
Yeah, definitely, and especially trying to find good motivating examples where, you know, training actually is useful on the embedded side. You know, that's something that would be great to see if people come and say, hey, I would love to be able to solve problem X, but I can't because I don't have training. Like, that really helps us too.
Okay. I have another question from Sergii. How do all TinyML folks deploy those devices in production? I think he referred to models. Do they use Tiny TFX?
So the funny thing about the embedded world is it often feels like going back in time in terms of automation and workflows and things like that, because they're trying to squeeze everything into really, really tiny devices. So there tends to be a lot of kind of manual kind of handcrafting of everything. And they don't tend to use much that we'd recognize in the way of kind of modern, you know, workflows. You know, this whole idea of continuous integration, and even, you know, often, you know, modern testing environments and things like that don't tend to be, and also devices are often kind of flashed in the factory once and then never touched. So there isn't that same kind of process of, you know, being able to do repeated deployments, which is one of the places where really having, you know, a pipeline helps. So in a lot of ways, it's we're still trying to kind of get the embedded world up on some like simpler stuff
Yeah.
before we I would love to see tiny TFX though. I love that idea.
So try to help me understand here. Let's say you build this model. At some moment when you want to put it into production, you want it really optimized, for example, for the device that's running on a battery. How is this optimization process going on? Is it something you do after you have the model? Is it something you have to consider initially when you build it? How do you go about that?
The most efficient way is really to start, think about it as you're building your model, because that's, it's like doing, it's like optimizing the algorithm versus optimizing the code. If you can shrink down the model at the model building stage, that's going to be way better than trying to optimize like kind of some inner loops of the software or something like that. So we try and offer a bunch of tools and a bunch of ways of telling how much space, especially because, funnily enough, it's actually often not latency, but it's memory size that is the biggest problem for deploying these models. Mm-hmm. So there are a bunch of things we can do, like, we offer quantization that is a big help for shrinking your model down. We also have some tools for removing things like layer names, like strings that take up space in your model. Mm. But the best way of getting started is just to have a really small model at the training stage. So, and that's kind of a bit of an art. We try and offer some examples, and we sort of recommend you start with like the examples for the particular domain, like an audio example or a vision example that we offer, because we've tried to make those examples as small as possible, but it's still definitely a bit of a dark art.
Interesting. Another question from, I hope I pronounced it well, correct, Kartikeya Portwell. Can we use TinyML TFFlow Lite for inferencing GANs models on the edge?
So, theoretically, yes. We have, I think, off the top of my head, I think we have the ops that you need for some of, depending on how you're doing your GANs, I believe we have the op support for at least some types of them. I actually haven't seen anybody doing this yet, though. I have seen people doing this sort of thing on mobile, like on phones. So if that counts on the edge, that's definitely possible. I haven't seen anybody doing it on embedded devices.
Okay, so that's another call for open source project there.
Oh yeah.
If anybody wants to bring it. A question from Tulio. What types of prerequisites should I attend to in a given project to find out if it's deployable in edge devices?
Yeah, that is an interesting question. I mean, honestly, the first thing that I try and do is just gather some data and just figure out if I can even train a model, no matter what the size, to kind of solve the particular problem. And then the biggest hurdle after that is, like, once you've trained a model, maybe it's like megabytes in size, then try constructing a really, really small model that's just a few layers and see how well it performs. And do all of this on the Python side. Like, don't even worry about trying to deploy it yet, but just kind of plan out a model that may, that fits within the memory budget, especially of the device you're looking at deploying on, which is probably only going to be a few hundred kilobytes, and try evaluating that model that size, training it and evaluating it on the Python side, and just figure out if the accuracy is good enough, because that will be kind of the most fundamental problem you'll hit. Then if it is good enough, the rest of everything else should just be a engineering, you know, like should be low risk in terms of, you know, it might be a lot of work, but like once you've verified that the machine learning model actually works, it's just a case of porting it over. So that's the way that I think about this anyway.
So get started and then optimize later.
Exactly. Like first thing is, can you even gather enough data to build a decent model? And then if you can you make that model small enough?
Cool. A question from Paulina. I love the Magic Wand demo. I wonder if it's possible to use similar solutions to do motion capture for movies and games.
I would love that. I would love to see somebody sticking Arduinos all over their body and playing Gollum or or something like that. I haven't tried that myself, but that would be a really interesting you know, project for somebody to take on.
Okay, I think we are running out of time. First of all, Pete, thank you very much for taking the time, joining from California. Hope's all good over there. Amazing presentation. And for everybody on the call, look into the GitHub project. Yeah, we will give some of Pete's books away to the good questions we had, and take the course. Get hands dirty.
Thanks, Alejandro.
Thank you. Have a good one.
You too.
And for the rest of the community, we will be back in 15 minutes, where our next speaker will come and present on the next topic that we would introduce there. Okay, 15 minutes break and see you. Bye. Okay, and it seems like we're back. Welcome everybody. Hope you are enjoying your dinner, at least if you're in EMEA, or if you're somewhere else in the world, breakfast or something similar, lunch, who knows. At least I had 10 minutes to enjoy my dinner very quickly. So I'm very excited to bring our next speaker. I think it was amazing segue going from Pete's talk to our next session. We're bringing in Luiz Gustavo Martins. He's a colleague of mine at Google. A pleasure to meet you, actually, because I don't think we have met before, even that we work at the same company. We have the same roots from South America. I'm from Chile, you're from Brazil, but you're based in London.
Yeah.
Cool. Have been 5 years at Google?
Yes, almost 6.
That's a lot. Yeah, that's a lot, right? So we normally say 1 year in Google is like 5 years everywhere.
Yeah.
but amazing. Yeah. And Luiz Gustavo Martins works today as a DevRel for TensorFlow. Has been at the role 1.5 years. And by concept, probably he's currently focused very much in audio and TinyML, and also how to put that in a TensorFlow Hub context.
Yes.
So, Gus, the stage is yours. Thank you.
Thank you very much, Alejandro. Hi, everyone. I hope you are having a great time. I'll try to keep up. After Pete, it's very hard. He knows way more than I do, but I'll try my best here. Today, I'm going to talk to you about TensorFlow Hub and how to use that for audio classification. And when we start to talk about audio, the audio domain by itself, right? There are a lot of challenges on this domain, lots of very good possibilities for machine learning. So, for example, when we think about speech detection, which is something that you probably use on a regular basis. If you use Google Assistant, there's speech detection. If you are using subtitles, caption, automatically caption generated, it's using, of course, speech to text. And of course, we can do audio classification, which is what we're going to see today. Or if you want to do audio or music generation, which is something super cool and advanced, you can also do using machine learning is here to help. If you want to do text to speech, that's when you need to, from whatever text you write, generate a voice saying that, which is also another challenge. The other cool one is speech detection. So if you sing or if you play an instrument, the model would be able to detect which pitch, which notes you're doing. And those are absurdly hard challenges to do without machine learning, because the audio field, the sound, it's not as easy to understand or to deal with as we imagine. So let's start. Let me just reset the counter here. Perfect. So let's start for what is sound. I know that the talk is about audio classification, but let's try to understand what sound first, right? Audio and sound are not the same thing. They represent different things. And sound, to be very blunt, it's the vibration that propagates on acoustic wave. I know that's a little bit hard to understand. So basically, sound is what you hear. Whenever there's an event that generates waves in a medium, we can take as air or water or a metal or table. When you do like this, whenever there is this event that generates a wave, this is called sound. And there are some properties that we would like to pay attention when we talk about sound. So the important ones are frequency and amplitude, and I'm going to use these terms later on, but we also have speed and direction. Of course, sound, it's absurdly important because that's how we perceive the environment, right? So that's how you know that a needle fell over there, that your TV is on, that's how you listen to music. But let's go a little bit deeper to understand sound. I mentioned acoustic wave, right? Let's go a little bit to math. I'm not going to spend too much time here. Don't be scared about the equation. So let's try to understand what's a sine wave. Sine wave is the sine function applied over time. And this is the equation over there, and that's what it would draw on a graph in the bottom part. Let me try to explain what are the important things. So the capital A there is for amplitude. And this tells you if it goes from, you can see the curve goes from 1 to -1, right? So this is the amplitude. It's, in this case, is 1, right? The other thing about sine wave is that it has a period. It keeps repeating itself forever, as long as you want to draw it. So this is the period, and the frequency is how many periods happen in 1 second, right? So this tells you how broad or short or narrow is the drawing. And we have the T is for time over there. The last symbol that I don't know how to say that, sorry. That symbol is the phase variable, and it tells you on the left side there, it's if the phase is 0, the graph from the sine function will start on 0. So if you put, like, I don't know, 1, it will start from 1 and then does the same thing, but starting from 1. So this is what this equation is. And why am I telling you exactly this? Why did we come back to the math class for a little bit? Because sound is basically a mixture of a lot of sine waves, all of them together. So if you see on the drawings on the right here, there are two. The first two are, let's say, very raw sine waves, right? I used that equation that I've just shown you and draw those two sine waves there. Just did that. There's nothing else. The third one is when I add the first and the second one, and I get the third one. So when we have a sound, the sound is basically maybe thousands of sine waves combined together for different periods of time. So if we want to get to a frequency, it's absurdly hard, because look, how do you do that for the third? How do you disentangle all these these frequencies? And okay, sorry, I saw the message. I thought it was for me. In the end, I hope I can answer any question you have. So sound is a mixture of that, and that's challenging, but that's enough for sound for now. Let's talk about audio. Audio is part of the title of the talk. So what's audio? Basically, audio is how you represent sound. So whenever you have a file that you recorded as sound, the file has now audio, because that's how you represent it. So when you represent this in a physical, digitally or analogically, when you record from the microphone, you are recording audio, right? And audio has some specific characteristics to it. One of them is sample rate. I guess you've seen this in sample rate. If you've seen, like, this audio file has 16,000 kilohertz or 44.1 thousand kilohertz. So sample rate is how many times you sample the air pressure in 1 second. So for each second of recording, the 16,000 will get 16 float numbers, one after the other, right? 16 numbers, one after the other, and per second. So that's how you represent audio. And if you think when you see, oh, CD quality, DVD quality, you just make the sample rate way bigger. So you get way more samples. So your audio is more clean. It's more close to what you really hear, right? So this is an important thing. There's another variable to audio, which is the channel. We have mono or multi channel, which multi would be stereo. So when we say that mono, is that we have samples for only one set of samples. When we have stereo or multi, we have other sets of samples at the same time. They're all together, right? And when you have audio, you form something called a waveform. In a waveform is basically, if you plot a waveform, that's what you see. Like there's a lot of lines over there because there's a lot of points per second. If you have the representation code, right? If you want to see the code, it's something like that. So it's an array of a lot of numbers. In this case, we have 750,000. For this is these numbers represent that waveform over there. So you have all of these float numbers that if you plot, you get this, and this is a waveform. This is what represents sound. But okay, so why am I telling all of that? Because I want to tell you about something called spectrogram. And what's a spectrogram? The spectrogram is the representation of a waveform over time. And it has more information than just the samples that we've got. So if we, the first graph over there is the waveform, and below it's spectrogram, right? So if we see the y-axis, sorry, I'm looking to two presentations. Let me look to just one. If we look into the y-axis, it's the frequency. Remember, frequency, that's something we care, right? If we look into the x-axis, it's the time. In the color, the higher the contrast of the color, the higher is the amplitude. Or this, you can say that, you can understand that as the decibels, how the kind of related to the magnitude of how high is the sound. So this, why am I telling all of this, right? And first question is, how do you convert a waveform to a spectrogram? I'm not going to explain that because that's kind of a half-hour class of audio analysis. And the basic here, we would use the Fourier transformation, not exactly it, but a variation. And then you do a lot of math over that. And that's how you go from a waveform to a spectrogram. But the other question is, yeah, okay, you were not going to explain how to create a spectrogram. So why are you even telling me that? Because this is one of the cool tricks about audio for machine learning. When we do machine learning models, we don't, and we have the inputs and we give the inputs to them. The inputs are not our waveform, not regularly. The model will try to understand is it will look into the spectrogram and it will try to find patterns in the spectrogram like an image classifier would do. So what we do is we get our waveform, convert to a spectrogram, and then we apply an image model to this spectrogram to extract features from it. When we have these features, then we come back and try to classify them as, I don't know, a dog or a cat or, I don't know, a siren or whatever, like someone speaking, a word. So this is how we do audio, do machine learning for audio. This is one of the ways of doing audio, machine learning for audio. You get your waveform, convert to a spectrogram, and then you apply an image classifier over it, right? You extract all the features, and that's how you would do that. If you want to do that by hand, there's this great tutorial that will guide you through getting the data set, working on the data set, getting the waveforms, creating the spectrograms, and then running that over a model that you run by hand. This is as close to raw as you can go, right? This works, it's fine. You are going to do a keyword recognizer, and it works, it's great. I highly suggest you go do that. But then there's a problem here. I just told you what to do, right? You can follow that guide and you're good to go. But if you want to go and have a better model, a more advanced model, a state-of-the-art model that people are talking about, or if you want to look into research, you need to go deeper. You need to go read some papers. Maybe those papers will get you to a code repository. This code repository might have something for you there. The problem is when you get here, it starts to get very, very complex because first you have to understand way more math than I just told you, right? You have to understand way more about machine learning than I told you. I didn't tell you much, but it will need you to understand that, to use these code repositories wherever they are. And then you have questions like, how do I try this model? What is, does it has any drawbacks? When should I use this model? Or is it the latest version? Do you have a sample code? To get all these answers from regular researching, it might take you a couple of days. So instead of learning something, you spend a couple of days trying just to get to understand what's written in the code. That's a lot of work and it's not productive. And that's where TensorFlow Hub comes to help. TensorFlow Hub is a repository of machine learning models that you can easily use. You have access to documentation, to multiple versions of the same model, to sample code, to all of that. I'm going to show this in a little bit, but you don't have to go through the journey of understanding everything by hand and suffering. We have all of that figured out for you. And that's why that's what I'm going to show for the rest of the talk and how it can help you with audio classification. Before we go to audio classification, let's talk about kinds of models we have on Hub. We have models for all domains. We have for image classification. So if you do proper image classification, object detection, image segmentation, style transfer, augmentation, pose detection, super resolution, all of those mods are available to you over there. We have also text, and text is an absurdly important field. We have all kinds of language embeddings, BERT models, classification models, all of that for you. Question answer models, we have all of those available in multiple languages. And of course, we have the sound models, or the audio related models for pitch detection, sound classification, embeddings for audio. We have all of that available. And more than that, we have them available for multiple kinds of deployments. So someone mentioned in the previous talk about TFX. Those models can be used on a TFX pipeline. If you need a language embedding to create your language model, you can just use one of the BERT models available. And we have also models that you can deploy on the browser using TensorFlow JS. We have models that you can deploy on mobile devices, as Pete was talking about them. You can have these models be deployed on a phone or on a TinyML, on a Raspberry Pi or on a microchip. We have Coral devices that are for, if you have the Coral chip, you can use those models. Some of them are specific for Coral, and those models are already available to you with documentation. And we have thousands of models available. There's a lot of them, and we are going to see some. If you want to use them, of course, we need to have some search and discovery. The models, you can just like a regular Google search, you can search for problem domain. For example, you can search for object detection models. It will show you a long list. If you want to search for image classification, sound classification, any of those things, they are all available there. You can filter them for example, if you want TF Lite model, which would be deployed on our own device for own device from mobile, or if you want a TensorFlow JS model, or if you want to fine tune. So you can filter by domain specific. So it helps you find your models. And after you found them, you can, some of them, not all, you can try the model right in the browser. For example, these ones, most of them are for image classification. So if you drag an image to the browser, it will tell you what the model would result, the result the model would give you if you try that on a Python code, if you download the model, right? So this is an easy way of trying models. We have the one on the top right, which is the SPICE model. I suggest you take a look. SPICE is for pitch detection. So the widget we have there, the demo, is you can sing to the microphone if you're brave enough, and then you can see the notes, because it's classifying the pitch and showing the notes for you. So this is a good thing to try, and you can try that right in the browser. This is one visualization of the documentation. You can see there's a lot of cool things there, and one important thing is there's the Open Colab notebook. Most of the models, they come with a Colab that you can click on the button, and it will open a Google Colab where you can try the model, all the codes there available. You can just run all and see it working, and you can play with it, change parameters, try your own data. That's easy. So the code for you to learn, it's there in the Colab, or sometimes in the documentation they have code snippets, and they also have information about the data set that this model was trained on, or they have information about which model architecture it's using, have information about if this model is good for the use case you're thinking. So there's all this kind of information, and that's amazing. But I've talked a lot about it. I did a very long pitch, sales pitch, and I know that as developers, you want to see things happening, you want to see them working. So let's go into two examples. I want to show you two examples of how we can do audio classification using TensorFlow Hub. The most basic one, let me guide you step by step. First, we are going to go to tensorflowhub.dev and open the website. We can see right in the beginning, if you scroll a little bit, we have a section about audio problem domains. You can just go to that section and choose which problem domain. So as you can see here, we have, for example, speech synthesis, command detection, pitch extraction, which is the SPICE model. We have speech to text. We have some of those. But what we want today is the event classification. When we click on event classification, we are going to see there are two models there. There's the YumNet, which is the one we are going to use. And there is this humpback whale, which is very new. It was published like, I don't know, last week before. And what it does, it classifies, it gets an audio and tells you if there's a humpback whale singing on that audio or not, right? So there's a cool story why we have this model and how it helps. But I don't have time to go into details here, so I recommend you go take a look. There's a blog post about that. That's very cool. So let's try the YumNet model. Suppose we click there. This is the documentation for YumNet. I hope you can see here. There's the collab button to the middle screen right side. There is the documentation. There is we have a version. The model has a version for TensorFlow JS, TensorFlow Lite, so you can deploy multiple environments. There's a model description. There is the documentation, which I'm not going to show you, but it shows how to use the model. There is, if you don't want to go to the collab, you would just want to see a code snippet. It's there. It will tell you how the model works, what is the magic. I'm going to explain what's the magic in a little bit, but it comes from there, so you can learn that, and you can see there's a link to the source code of the model, so you can click and see the complete source code if you want to understand more. But the important thing here, you don't need to do that. If you want to just use the model, you can just do this here, right? So how do we do sound classification? I'm going to go over these 6 lines of code, and then you tell me if it's how hard it is. We have 2 lines which are import TensorFlow and import TensorFlow Hub. With that, we have the dependencies to use a TensorFlow model, right? TensorFlow Hub is more than a repository of models. It has also a library to help you load these models and use them. So it makes your life easier. As you can see here, there's no download anywhere, and you should never worry about that. So the third line, where we define a handle, I'm going to do something ugly, which is this coming back. So if you can see on the top, on my URL over there of the browser, there is a URL, right? That's the model handle. So this model handle we can see here is exactly the link to the model on Hub. So if you have this, you can just follow this link back and read the documentation. Or if you want to use any model from Hub, you find them on Hub, copy the URL, and you call the load method that you see right on the 4th line. What load method does, it will get this model for you and load it to memory and leave it ready to be used. You don't need to do anything else. So when you use TensorFlow Hub, when you see TensorFlow Hub code, you might see the import TensorFlow Hub and the load. Those are the 2 lines of code you're going to see. There are some others. We're going to go into another one soon, but those are the most common lines you ever see for Hub, because that's it. You load and that's it. On the 5th line, we have this load my sound file. This is, I'm cheating a little bit here. Why I'm cheating? Because this method doesn't exist. You would have to load the wave file. You have to do that. And you have to do another thing. You have to convert the data to the format that the model wants. YumNet uses wants a wave array of float numbers, like the waveform I showed before, but with a specific sample rate, which is 16,000 kilohertz. Most of the audio models do exactly the same, 16,000. So if you have a higher quality, you have to lower the quality by yourself. I'm hiding that because it's a boilerplate code. And it expects a mono channel, so it has to be like only one waveform, and that's it. If you can do that, you load the waveform. You have an array with thousands of floating numbers. You give this to the model. Remember, model comes from hub.load. Model give the waveform. That's it. The model just did the inference for you. The output of this model is the scores, embeddings, and the spectrogram. So the score, let's go from backwards. The spectrogram is what you see on the second drawing, the second square over there. It's the green yellowish thing there. That's the spectrogram that was created internally by the model to do the inference, right? So it gives you for free, so you can visualize, debug, whatever you want. So it's not all models do that, but I really like what they did here. So that's why I'm showing. The first square, of course, is the waveform. So if you just do plot or show, it will do that graph for you automatically. Spectrogram, almost same thing. And the last one are the scores. So the scores tell you which class did the model detect on each part of the wave file. So it doesn't give you a score for everything. It gives you a score per part of the wave file, because audio is something that happens over time. So I'm speaking, then there's a silence, then there might be a car, then there might, so for each part of the wave file, it will tell you, look, at this part, it was a car, a horn, a dog, lion. Well, if you have a car, lion, and a dog in the same audio, it's a weird place to be careful. But that's what the model will give you back. So you have the scores there. You can see the darker the square, the more certain the model is about a class. I don't know if it's easy for you to read, but you can see the first 4 classes it gives you. It's animal, and then it's domestic animals, pets, and then it's cat, and then it's meow, and that's the four, right? So this was a cat meowing, of course, and you can see it gives you in the top 5 there is the answer you want, and this works. It's great. Yeah, that's amazing, and that's it. But let's go deeper. What if you want to do audio classification for your own audio, for your own classes, for whatever you want? So you can do that. You can do that using something called transfer learning. The gist about transfer learning is you have models that already do some work, and it's a work that's similar to what you want, but it's not exactly what you want. So for example, let's give the image example so it's easier. You have a model that can classify among 1,000 classes. So it knows what's an elephant, what's a bus, car, building, whatever. But you don't want that. You want a model that can tell you if it's a cat or a dog. This model that does 1,000 classes, it might tell you there's a cat or a dog, but it might tell you a lot of other things. And when you want to use this model on your product, you don't care about the other things. You care about cat and dog. So what you can do is you can use this big model and specialize it for you, for your data set, for your images. When you do this specialization, this is called transfer learning. It's like there's all this knowledge here. I'm giving this to a new model and re-explaining some things to it. Say, hey, this is a dog, this is a cat. So you do transfer learning is another training of a model, but with a specific data, with your specific data. And this is an absurdly powerful technique, and we're going to use that. You can think like if you know how to code, for example, in Java or C++ or those languages, if you want to learn a new language, you don't start from scratch. You kind of know what's a conditional, what's a loop, what's a variable. You know that already. You're just adapting your knowledge to a different spec. So if you're coming from Java to Kotlin, for example, you need to learn some new keywords, but the idea is very, very similar. And this is like transfer learning for language, programming language. So this is kind of the idea. Same thing for if you know, I know Portuguese, right? So if I try to learn Spanish, which is similar, it's easy for me, not easy, it's easier than someone that doesn't speak any Latin language, because I kind of get the idea of some things. So there's a transfer learning happening here, right? What I'm going to do now is there is this example that does exactly, it's the full code of what I'm going to talk. So if you want to copy and do it by yourself later, I highly, you should definitely do that, because it gives you much more information than I have time to do right now. So what I want to do is I want to get YAMNet's model and make a classifier for dogs and cat sounds, audio. And as I showed you, YAMNet knows what's a dog and a cat, but it also knows that what's a pet, what's a house animal, and all these other things. So if I need to have like do a classification in the field, and it tells me, look, it's a pet, and it's an animal, but then it's a lion, I might run, and if it's a puppy, I might stay, right? So that's the difference here. So that's why we're going to train a model for dogs and cats that's going to be more precise because it's less generalist, right? YAMNet classifies, I skipped one slide. So YAMNet is a model that can classify between 521 classes. So that's a lot of classes. It was trained on a lot of data. So it's a very generalist model. It's a very good and fast, but if you want to make more specific, we can do that. And that's what we're going to do. On that collab, we are going to use a data set called ES50. I don't know if I wrote it. Yes, I wrote it. So ESC50, which stands for Environment Sound Classification. It consists of 50. There are 50 classes of audio there, and with 2,000 recordings. Each class has 45-second segments of audio, and that's what we are going to use. So this data set is already clean on the proper format. Already, they have already a way to break into train, evaluate, and test. You might need to read the documentation. I'm not going to details here, but it gives you all of that. So it's a good first data set to use because it's easy to use. It's small enough so you can play with that. And all these audio, they came from a free sound project. So if you search for free sound, it's a website where people can contribute with audio about any kind of things. But using from free sound doesn't do all the curating like the SC50 did. They get this audio, convert it to the same sample rate. They already split into 5 seconds. The free sound is like anyone contribute whatever they want. It helps, but you cannot use directly for your model, right? It needs some pre-processing, and the people from ESC did that for us already, so that's great. And what we are going to do for this is we are going to use YAMNet to extract the audio embeddings. What's an embedding? So what's an audio embedding? So for each audio part, we are going to convert that to an array of numbers. And audios that are similar, they should generate an array of numbers that if plotted into the hyperspace, they should be close to each other. The same idea as text embeddings, where similar text, when you convert to proper embeddings, if the embeddings have a good quality, if you plot, they're going to be close by. Same thing for when we apply an image classification model and we get the feature vectors. These vectors are arrays that if plotted, they are similar. If, for example, if you classify an elephant, all the elephants will be similar. So we are going to do the same thing for audio extraction. We're going to apply YAMNet to extract these embeddings, and then we're going to classify these embeddings with a classifier. How does YAMNet works internally? What it does is, first of all, it gets your audio, creates a spectrogram. As I mentioned before, spectrogram is the key. And then it will create frames of 0.96 seconds, and which is the yellow bar over there. And it will, for each frame, it will extract 1024 float, an embedding, which is 1024 floating values, right? And then we skip 0.48 seconds. So we do a hop, and then we do the same thing, extract embeddings from there, another hop, and that's exactly what the image is showing there. So for this use case specifically, it returns to me 13 features, 13 audio embeddings, right? These 13 audio embeddings I'm going to use to explain to my model what's a cat or what's a dog, right? Let's see some code. I'm talking a lot about stuff. How do we do extract features here? First of all, when we deal with audio, it's different from other domains because we load the audio to memory, and then we apply some transformations on there. Depending on how we do that, we cannot load all the audio available, right? I have to rush it because it might not fit in your memory. So that's why we use TensorFlow data set. that you can load. It lazily loads stuff for you if you use the map function. So the other thing we can do is we can use extract embedding map to extract embedding function in all your audio files, and it will run YAMNet module for all your audio files. Even if you didn't load them to memory yet, you're creating a data pipeline that's only going to be executed when you run your model, when you start training of your model. Here, I'm just showing the code to do same thing. YAMNet, receive wave data, extract things, return the embeddings. Simple as that. Next part is how do we train our model? Our model is simple. It's a sequential model that has received a batch of embeddings. You can see shape 1024 there. And then have two dense layers. It can't be simpler than that. Two dense layers, I will compile fit, and then when I evaluate that, I'm getting close to 85% accuracy. Look, 85% accuracy for what we did here is a lot because we didn't do much, right? We didn't have to create our own super complex model. And we have a very good already. 85% is very, very good. But there's a problem with our model. If we look at the input of our model is audio embeddings. You don't have audio embeddings in the wild. You have audio files. How can we fix that? We can fix that by ensembling a model that has an input layer, and the next layer is the YAMNet model. So we are using the other TensorFlow Hub method, which is Keras layer. It loads your model ready to be embedded in as a layer in another model. So what will happen here is we are creating the Keras layer with YAMNet handle, same handle we've shown before, is the same. Use of load in Keras layer is the same model handle. And then I'm using the function API here. I use that to extract embeddings. These embeddings go to my model, and then I just do a reduce mean layer. Don't worry too much about that, just to make the result easier to read. And then I have my model, and I save. So I am concatenating like the YAMNet model from Hub as a Keras layer to my model, and I have a full model that I can deploy anywhere. I can just use this on a server. I can convert this later to TensorFlow Lite, use on a phone, and that's it. If you want to see all the code is on that tutorial that's over there. That's it. You just created an audio classifier, and with this code, and it works, and it have like very, very good results. Let me go into some more details on how TensorFlow Hub works internally. Whenever you request a load from Hub, it will go to our servers, download the model locally. When it downloads a compressed version, it uncompresses to an internal directory that you can change using an environment variable if you want. Otherwise, it's in a temp directory. You usually don't need to access that. And what happens is when the directory, and when you call load again for the same model, it will look, oh, I have that already here, so it doesn't re-download. So you don't need to worry about downloading, consistency. All of that is dealt for you. The library gives you all of that. And that's it. That's as simple as that. You don't need to worry about any of that. Just to finish, we have supports for TF Lite modules, TensorFlow JS, as I showed before, aside from regular TensorFlow. Models on Hub, they are not always from Google or DeepMind. It's from multiple companies, from the community, from GDE, from Kaggle competitors, from a lot of people. So if you want, you can publish your own model. Of course, feel free to do that. And what I want to leave you is TensorFlow Hub is here to help, to support you in your journey to solve a problem. There's a lot of possibilities here. And for example, you can do hackathons to use on hackathons. For hackathons, you don't have that much time. You can use a pre-trained model already easily to do some classification. You don't have time to train a big model during a hackathon. You have to use models available, and it cannot be faster than TensorFlow Hub because the documentation is there. You don't need to understand other people's code too deeply. So hackathons are great. Using, of course, on your work, if you need a language embedding or anything to create your own product, go ahead, use that. Kaggle competitions, you can create a benchmark model to say, oh, let me try the easiest here. And then you have a benchmark, and then you can try to beat that on your own or submit with Hub's model if you want. So there's a lot of possibilities. I guess I'm a little bit over time here. Sorry. Thank you very much. On Twitter, if you have any other questions, and please take a look on TensorFlow Hub. I'm pretty sure it can help you. Thank you.
Thank you, Gus. Thank you for the very interesting topic. Complex stuff in between all the math and the Fourier series, and a great invite to also contribute more to TF Hub. We do have some questions from the audience, so let's
Perfect.
start with Frank. Frank Mervert. Sorry if I pronounce it wrong. Would you see a use case for sound classification also in the quality assurance in a manufacturing process?
That's a very good idea. It can definitely be used with that if you have the data, which is the problem. But that's also a very good idea because remember, you can use for sounds that we don't even hear, right? Some sounds we don't hear. You can use the same if your microphone can capture that. You can use those to train a model also, and you can have a model that can work on the silence, right? Because technically I'm not hearing some frequencies, but it can give you results even there. So that's a good idea. I definitely think it could work. The only barrier, I would say, is that the data set. If you have the data set, it's annoying to get a proper data set with events well classified, but that's a good idea.
Cool. I think we have a question very similar from Tulio, where he says, Yamnest use audio signal embeddings on one of its output. Would it be possible to create embeddings in a similar way for vibration signals?
Yeah, I guess same idea,
yeah. Then we have Sergii. Sensors can generate quite a bit of noise. Does it affect accuracy of audio models more than image models? And do we need to factor in the difference of noise among different sensors?
So that's a good question, and you have to think like that. If you want to deploy your model on a field where there's going to be this noise, you want this to be on the data, because then you'll have a more realistic situation of what's going to happen in real time. The other thing you can do is you can create a noise class. So you can just start recording like how is the environment, like a Starbucks environment. You just record Starbucks all day. This is your background noise. And then your module can learn, oh, this is background noise. And then it's easier for it to learn later if there is a cat or dog there, because it will background, oh, there's a dog and cat because I can see it's different. So you can use this background noise to help you, but depending on how you do, you don't even worry about it. You just, the module figured that out. But the answer is that depends and needs to be tested. But the noise could be part of as a class.
Mm-hmm. Cool. A last question from Yusuf, maybe more related or also related to TF Hub. There are less audio models compared to text image on TF Hub. Trying to inspire my community for more work on audio, but we will also have a bigger effort put by TF team. Or the question is, will we also have a bigger effort put by the TF team, maybe forming a SIG on audio?
That's a very good question. Hi, Yusuf. So the question is, we try to get as many modules as possible. The problem is that people do more text and image. That's how it is today. So I'm trying to make audio more popular and get more people to contribute the modules. And this is a challenge, and I love for people for the community to contribute back. I'm trying my best to get more teams in Google to publish their own, because we have another of other models that are not there yet for whatever reason. I'm working with them to get those models, and I agree that we need more of them. We need more speech to text. We need more other audio classifications. We need audio generation. We need all of those, and this is a work in progress that we're doing. So bear with us. We are improving that, and I completely agree that we need way more than what we have today. But that's that's a step-by-step, right? So I guess giving this kind of talk, showing the importance, the community telling us, hey, look, this is nice for multiple reasons. For example, for accessibility is an absurdly good use case. For example, if I have a phone and I'm deaf, I don't listen to things, right? So if there is a alarm, I'm not going to listen to that. Or my phone is too high, I don't listen. My phone could blink and say, hey, there's something going on, please pay attention. So this kind of accessibility perspective, only audio classification can help you, right? So this could be another thing that we could use. But yes, we're working on that.
Okay, and I think also the call again is, as community, of course, you're more than welcome to contribute with your whatever you're doing within the company you're working at or research institute and so on.
And even if you don't contribute a model, you can publish blogs about that, mention that on social networks, so you get more people. Because when I talk about TensorFlow Hub, sometimes people say, well, I didn't know this existed. And it helps a lot, so you can just use that and tell others, so people, oh, that's a good idea, maybe I should try. And the more people come, more people contribute, it's better for knowledge sharing, right?
Cool. Super. I want to thank you, Gus, for taking the time and sharing your knowledge and what you are looking into. And thanks for all.
Thank you very much, Alejandro, for the invite. I'm very glad. I hope people enjoyed. If you have any more questions, please ping me on Twitter. I'll be there anytime. Just send a message. Always glad to talk about it. Thank you very much.
Thank you. And we will be back in 12 minutes at 7:15 with our next speakers around MLOps. Look forward to that. In between, a little break. Either go grab some food, coffee, but don't miss the next session.
Hey everyone, I hope you guys can hear me. It's great to join you. Sergii, I couldn't hear you. There's something going on with the connection, but I hope you guys can hear me. And
Okay, does it work now?
yeah,
Oh, sorry. Like I think like there was some technical issues. But anyway, like what I wanted to say is that you wrote amazing book about NLP, right? You wrote amazing book about machine learning in production, and I think it's like really good transition from like us building the models like for tiny devices, us like kind of like building that with TensorFlow Hub, and now actually bringing it like into full cycle from data shifts, right? From actually bringing this like for long-term better of humanity. So please take your stage, and sorry again for technical difficulties.
No worries, Sergii. Thank you for having me. It's great to be here. Great to be part of the wonderful TensorFlow event. Here we go. My name is Hannes. I'm a machine learning engineer at Digits, and I'm also a Google developer expert for machine learning. As Sergii mentioned, I had the chance to co-author 2 publications. One is about natural language processing, and the other one is about building machine learning pipelines. And here at Digits, I have the chance now to combine both of my interests to build machine learning models which are in production, and then we use a lot of NLP to analyze financial transactions. So today, I would like to talk about like how we use machine learning, and in particular TensorFlow at Digits, and how do we accelerate our machine learning projects. And as Sergii mentioned, we focus heavily on taking business problems, solving them with machine learning. And then we have always this problem where I often say like the machine learning problem starts when you release a machine learning model, when you deploy the machine learning model. Like how do we update those models? How do we test them? How do we serve them? This is something I want to focus on today. You might wonder, what is Digits? So just to give you a quick summary of Digits is, it's a real-time engine for business insights. So companies come to Digits if they want to understand their businesses better. Normally they would go to their accountant, they would ask some questions, and here we're using machine learning to drive some of those answers through machine learning and give those companies a much faster time to the answer instead of going through the accountants and looking up things manually. So when we take a look at machine learning in production, we're very lucky these days that there's slowly like best practices emerging. Obviously, there's large companies out there like the Googles, the Facebooks. They develop tools internally. They have been using those tools internally for a long time now. And some of those tools become open source. I want to present a bunch of those tools in the talk later. But before we get into what's the current state is and what the ideal state should be, let's talk about what the state at most companies is. And so there is like a static data set, maybe coming out of a database. We train then maybe in an IPython notebook, some machine learning model, whether it's PyTorch, TensorFlow, scikit-learn, doesn't really matter. But basically we have a model, right? And then at some point, we just throw this model over the fence, potentially to a backend team, and he's like, here you go, right? But this has like huge flaws, right? As probably most of you have discovered, there are security aspects. Data scientists, you have like those data science mic drops where the data scientist can just walk out and there's nothing documented. We have those code entanglements where if we load machine learning models in the backend code, then they need to be shipped with like backend commits, and we would like to separate this so that data science teams can deploy it in different time horizons, independently from, let's say, backend teams, for example, or potentially the front-end team if you want to deploy a machine learning model in the front end. There's like no reproducibility, or nothing really enforces the reproducibility of those models. Just because you have a notebook doesn't tell you if this is the last state, or it doesn't tell you if potentially somebody else changed pre-processing steps or hyperparameters, etc. And then you have all these like crazy things of like data scientists want to do data investigations. They want to explore the data. But if you do this, for example, on a production database, that could have customer impact. You can't really do this. And at the same time, then a lot of data scientists say, okay, I'll take a copy or take a dump of that data set, and they run this locally. And then you always have this concern of like, what happens if there's a physical theft of my machine and somebody walks away with like the data? And at Digits, we're handling financial information, and we take that topic very seriously. And so this is very top of our mind, and we want to avoid those scenarios. And in this presentation here, I want to show what we have done so far when it comes to machine learning to prevent those scenarios. Just looking back a couple of years, this is a tweet from 2018 from a machine learning conference where one of the organizers was tweeting a quote from a presenter and saying, hey, it's like really easy to get to a machine learning model. It takes like 3 weeks, but to get the model out, it still hasn't happened after 11 months. And that is a very common topic. So you might think this is 2018, we're in 2021. We're a couple years further, but there's a recent tweet from a couple of days ago where somebody said like it's indefinitely easier or infinitely easier to get to a proof of concept than getting something out into production. And I can emphasize with that, there's a lot of things you need to consider. And as I said earlier, sometimes the machine learning project only starts when you deploy your machine learning model. So when we looked into machine learning at Digits, we then had some thoughts about like what should our ideal environment look like. And this is in the next couple of slides, I want to show you some summaries or a summary of like what we decided, and that has worked for us really well so far. So as you probably have seen in the past, there's this psychology sort of like concept of the Maslow's hierarchy of needs, and clever folks have like converted this into what that would mean for data scientists. And we spend a lot of time talking about the very tip of that triangle. So we talk about machine learning models, deep learning models, AI, crazy topics. But to actually get to this point, we have to fulfill all the other layers below. So no machine learning project makes sense if the data is not very clean, or like we're not very, we don't really have a good experimentation set, or we don't have not the basic infrastructure ready to do all the machine learning work. So what we have done is at Digits, we try to make sure that we have all the foundations ready when we build our machine learning projects. And again, I want to show you some examples here. But we set up like 10 sort of like checkpoints where we said this is our ideal environment. So we want to focus on like the data access. We want to prevent the business impact. As I mentioned earlier, customers should not face any particular impacts. We want to give data scientists, but also the flexibility to run experiments, to investigate the data easily. We want to prevent those data leaks that accidentally not just data leaks from one data set to another, that we talk about this later and when we talk about testing, but we also want to make sure that data doesn't leak onto local machines and things like this. Experiment tracking is really important for us when it comes to knowledge sharing. Data analysis and like this whole model updates, automatic model updates is key because we don't want to burden data scientists too much with updating those models. And then the whole thing about like tracking machine learning models, what goes in, what goes out, testing models, and then also an easy deployment is really important to us. So in the next 30 minutes or so, I want to guide you through some of those or through all those checkpoints and show you what have we implemented on our side to solve those issues. So in the very first case, we talk about data access. So for us, it's really critical that data scientists and machine learning engineers have access to a non-stationary data set. So the data is changing constantly. We're onboarding new clients. We see new transactions every day, and we want to make sure that all the models we run, they're up to date. And working with a static CSV file doesn't work for us. So what we want to do here is like, we want to give data scientists the ability to have data access, but we want to separate them from the actual databases where we run our customer queries. So the way we do this is we have like a data repository for our machine learning engineers and data scientists. And this could be like a copy to BigQuery or a copy to like a feature store where you could, for example, use Hopworks or Tectron or something like that. And then export as often as you can what makes business sense for you. So if it's daily, if it's weekly, maybe even like twice a day or whatever you prefer. And in those exports, you can build in very common transformations. So for example, if you have timestamps, in that moment, you can convert those timestamps into like day of the week, or you separate out like certain timestamps, hour, minute, and so on. Whatever you want to do. What I wouldn't do in this moment is like very model-specific transformations, and I'll show you something what you can use for those model-specific transformations. So with this, you already have your data access clear, because if you run your queries in like BigQuery or in a feature store, data scientists don't have to run those feature transformations locally. They can do the investigation in a cloud environment, and therefore that solves your permission issues. And also, you sort of encapsulated the data science repositories, or the data repositories for the data scientists, and you basically prevent the business impact there. So if we run like a long-running query, which takes maybe a couple seconds, we're not taking down the production database, but we can run this with production data. Then the second step for us is which is also really important, is we want to give data scientists the ability to run machine learning experiments really effectively and also efficiently. And then what that means for us is we're running notebooks in a cloud environment, and you can do this with like GCP's AI platforms. They provide you notebooks, or you can run Jupyter Lab within your Kubernetes cluster. It doesn't really matter, but the key is don't run them locally on your local laptop. You could basically use a really cheap notebook, just access it through your browser, and then work on those cloud notebooks. And the advantage there is you have almost unlimited access to hardware, so you can switch between CPUs, GPUs, and potentially TPUs if you need to. And then you can also directly connect to the data repository. So for us, this is a really good environment. We can rapid prototype our models. We get to an architecture, and then we can take the next steps from there. So with this, we have the ability to say, okay, we have flexible machine learning experiments, and we can also prevent those data leaks, because the data stays in the cloud environment or in the on-prem environment, wherever you run your data repositories, but it's not going to my local laptop. And those are the scenarios we want to prevent. The next thing is like, we want to track our experiments, which we run in those notebooks. And the key thing here is, when we talk about experiment tracking, this is a form of knowledge transfer. So my colleagues should know what experiments am I running right now. And if we pick up a project maybe 6 months down the road, we should build on top of what we have tried today and what worked. So anecdotally, we can share some information there. But experiment tracking is really great if we want to take a look at what were the exact hyperparameters, and comparing runs, annotating some of the information we put in during our experiments. And so if you want to do the same, you can track all your experiments. You can share them with most tools in your team. And then you can also, what I would highly recommend is, whatever tool you pick, focus on the automation of the tracking. So you shouldn't set up like a complex setup to track your experiments automatically. If you use Keras, I would expect that most tools support like callbacks, and that take all the information from there. Tools you can use, there's replicate.ai, and then there's weights and biases. Both of those tools are really good. Some of them have pros and cons, but they solve that overall problem of like knowledge sharing of those experiments within your team. And with that, we have checked off the box of our experiment tracking. So with the top row, we basically sort of like have access to production data. We can experiment, we can come up with proof of concepts. And now it's time to take a look at like, how do we take those proof of concepts and turn them into production machine learning models? We have the great ability these days to stand on the shoulder of giants through transfer learning. And TF Hub is a quite essential tool for us to get to those proof of concepts really quickly. So for example, we can go to tfhub.dev, investigate what models are around, what's the state of the art these days. what models can be fine-tuned, what models can we use as like pre-trained models without fine-tuning. We have the chance then also to try them out really quickly. I would highly recommend checking out TF Hub. If you use other machine learning frameworks, you can also use Hugging Face if you're interested, or if you're in the Keras and TensorFlow world, as I said, TF Hub is the place to go. The integration is really easy. This is a recent example of like how you can use BERT. If you go back like 12 months ago, it was fairly tricky to use BERT as an NLP model. You had to sort of take your raw strings and convert them into the BERT required data structures where you have your input masks and your segment list, segment masks and things like this. You don't have to worry about this anymore. Google gives you now a pre-processing model also coming from TF Hub, and basically with a few lines of code here, you can then, this is only showing you the pre-processing step, but you can add one more line where you basically infer your encoder, and you basically, that's all you need to do these days to go from a raw string to a BERT inference. So then the next step what we want to focus on is like using TF Keras. By going through TF Keras, instead of using the traditional Keras, we get the ability of, or we get the advantage of various optimizations under the hood. And Keras itself gives us the chance of reducing our boilerplate code. At the same time, we get the great opportunity to write custom code. And we do take advantage of this quite extensively here at Digits. We write custom layers and custom models for various functions we need for our machine learning models. The great thing is, under the hood, everything runs on the safe model format. So all the tooling we're showing here is based on the safe model format. So even if we, let's say at some point we switch to JAX or something like that, we can then use the same tool chain as I show you in this presentation, as long as everything is based on the safe model format. So this is a example from the documentation of like how you can quickly write a Keras layer. As you can see, it's fairly straightforward. You basically initialize whatever variables you need, and then you have like a call function or call method in this case, and then you describe what that layer is supposed to do. We have like specific layers for some of the training aspects we do, and writing those layer functions has been really good and allowed us to really focus on what is the key thing. All right, so then now we basically have our proof of concept. How do we take our proof of concept to a production machine learning model? And the key tool what we use here is TensorFlow Extended, abbreviated with TFX. Basically what we want to do is like we want to give data scientists a chance to forget about the machine learning models they developed. So over time, we know that machine learning models or the performance of those models, they decay. The world around it is basically adjusting to that machine learning model. Folks figure out like, hey, this model is predicting something, so let me try if I can get better results. You can see if they can try if they get better results if they sort of like change the input data. You can see this over time. This is something which is worthwhile watching. And over time, it's good to retrain machine learning models to really keep them up to date with the expected behavior. So those model updates can then be time consuming. And here the focus is on the automation. What we want to do is we want to basically write a pipeline where we can trigger that pipeline every couple of days, whenever new data is available, and retrain this machine learning model, and that produces a model candidate. If you want to do the same, you can use TensorFlow Extended, or you can use Kubeflow Pipelines SDK. The later SDK works with basically all frameworks, but you could do the same with TensorFlow Extended. You can now write custom components, and those components they're not like framework dependent. And so to say, you don't really have to train a TensorFlow model anymore. So people might ask, like, why do we need machine learning pipelines? I just want to reiterate this because I think that's really critical. When we build our machine learning experiments in notebooks, this is more or less like a car model, like as you can see here in this photo. The focus here is on the architecture. We want to figure out like what architecture sort of works. Is this model converging? Often we're training our experiments with a small data set just to get something off the ground to see, can we solve this business problem? But when we want to go to production with this machine learning model, we want to turn this into a real production line where everything is automated. We produce machine learning models frequently according to a certain spec. And that spec comes from the experiments we have done manually before. When we talk about automating our machine learning lifecycle, that basically summarizes this like endless cycle going from the data, we do the data validation, data preprocessing, feature engineering, model training, model analysis, and validation. And then once we have our models validated and analyzed, then we deploy them, capture more data, and retrain our machine learning models with the next cycle. When we take a look at TensorFlow Extended, we can express the machine learning pipeline through TensorFlow Extended. And TensorFlow Extended gives you two options. You can use portions of TensorFlow Extended as standalone libraries, and I'll show you some examples in the coming slides. But you can also express all the steps of a machine learning pipeline through components. And then I'll show you in a second here, you can then coordinate the execution of those components through orchestrators. So this would be an example of like, how does it work in TFX? So basically you describe every component or every step of your pipeline as a component. And then we have the chance to run and execute the pipeline through orchestrators. That could be Apache Beam, Apache Airflow, Kubeflow pipelines, or you can even run it in your notebook. And then the cool thing is, and we'll talk about this in a little bit more in detail in a second here, we can then also store information in a metadata store and track exactly what goes in and out of our pipelines to make sure that we track all the artifacts for our machine learning model. Why should you focus on TFX, or why should you pay attention? So first of all, it gives you the functionality to express machine learning pipelines, the entire pipeline lifecycle. You have the chance, the key difference with TFX over other tools is orchestration agnostic. So for example, in the case of Kubeflow pipelines has to run on Kubeflow. However, if you use TFX, you can then orchestrate it with Apache Airflow, for example, if your company is already using Airflow for ETL processes, or if you're running Apache Beam heavily, then maybe it makes sense to orchestrate your machine learning pipelines on Apache Beam. The metadata is really at the core of that framework, where everything which goes in and out of those components is registered by a metadata store. And I think this is really critical. I think there will be a lot of attention on this in the future when we talk about traceability and sort of reproducibility of machine learning models, that we actually know what goes in and out of those machine learning models when we train them. And then this great tooling is the great tooling of TensorFlow Extended allows us that we can distribute our pre-processing pipelines. So they run on Apache Beam, and we can then scale Apache Beam on GCP Dataflow, Apache Flink, Apache Spark, to really scale up data preprocessing when we do the feature engineering, the data validation, the model validation, et cetera, et cetera. So this gives us great functionality to really distribute our testing here. TensorFlow Extended is very easy to set up. You basically have individual components you load, you set them up with parameters. So for example, in the first code line, you see that we basically load data from a folder. In this case, we would expect CSV files. Then we take the output of that step, and that gets passed to a statistics component, which generates basic statistics over our data sets. From those statistics, then we can generate a schema and figure out it has a schema change. And then later on, we can then apply our transformation steps, which we have defined in our module file. It's very condensed code, as you can see, but it's extremely flexible in that sense of what we can express. We can have branching pipelines. We can have conditions in pipelines of like, use this machine learning model if it's better than the previous one. You can take a look at like models can be blessed You can make conditional deployments, etc., etc. So it's highly flexible. I want to spend a few minutes here and just show you two two libraries within the TensorFlow extended framework to just show you how powerful this tool is. One question is always like, what is the underlying statistics in the data set? And so with TensorFlow data validation, you can easily get data insights. You can just run 2 lines of code. I can show you this in a second here. And you get like really good statistics to see, okay, what features can I use as dense features? Where should I be more careful? Which features are sort of sparse? What's the distribution? You can compare data sets, etc. You can then also use this as a standalone library in a notebook, or you can you can do the comparisons in your notebooks. In your pipelines. If you don't want to use TensorFlow Extended, that's totally fine. There are other tools out there. One of the other tools is called Great Expectations, which provides you similar statistics. So just to show you how easy that is to use TensorFlow data validation, basically you load your data set. You can load from various forms of data. You can load from like pandas data frames, from CSV files, from TF records. There's a lot of entry points there. And then basically with 2 lines, you generate the statistics. And the second line here, you visualize the statistics. Then you get like a really rich summary of the data. Might be not impressive for statisticians, but like for data scientists, machine learning engineers, especially when you start up with a machine learning projects and you want to get a good intuition of the data set. I think I really love those statistics, and it helps me to understand the business problem better and see potential pitfalls. You can then also compare data sets. So in this case, with the code shown here, you can then compare it against a valuation data set. And that gives you a chance to overlay those statistics and the graphs. How does it look like in reality? So this is a screenshot. You get like basically 2 tables, one for numeric features and one for categorical features. They have different charts and different metrics. But the really cool thing is you can see like how many values are zeros, how many are like duplicates, how many unique values, etc. And then also how many are missing. That gives you often a good impression of like, can I use this as a reliable feature in my machine learning model? A library I want to also point out is TensorFlow Transformation, or TensorFlow Transform. It's the most underrated library, I think, in the TensorFlow ecosystem, which is pretty extensive. But this is a real workhorse we use at Digits when we write our machine learning pipelines. The key thing of TensorFlow Transform is that we can express our pre-processing steps as TensorFlow graphs or graph ops. And normally during our experimentation, when we do our model training, we do some sort of like quick pandas manipulations of our data sets. And then we train our machine learning models. When it comes to production, it is extremely helpful to express those pre-processing steps as TensorFlow ops. You might wonder why. And the key thing is you get 2 benefits from this. Number one is the output of those pre-processing steps is a transform graph. And when you export your machine learning model after the training, you can combine those 2 graphs, put them together, and export them as one artifact. So in this scenario, you can then you can say, hey, great, I only have to ship like 1 artifact. The model takes raw input, converts it internally into whatever we needed, and then makes the prediction and the labels come out. The second benefit is when you apply TensorFlow Transform over your training set and validation set, it will do 2 passes on the training set. First, it will go through the data set and find out the important characteristics of your data set, and then it will do a second run and apply those characteristics with the transformations and transform your data set into a transformed data set, which means during the training, you can save the time. You don't need to reapply the transformation steps. You can just run over those data sets over and over and over. It also runs on Apache Beam, so that gives you the chance to really distribute those feature engineering steps. And you get a lot of like predefined functions for your usage. So I show you an example here, which is pretty rich in terms of like the implementations already. So this would be an example where you say, okay, I have a couple of reviews in my NLP problem. I have a raw string. I want to split those strings into like word tokens, and then I want to apply like a vocabulary and then build a TF-IDF vector out of it. And normally that would take like a couple of good lines of code, or like dependencies to other TensorFlow or to other Python packages. But then there always is the problem when you update something, you have to retrain. And here in this case, everything happens basically in this one pipeline. If you make a change to the pre-processing steps, that invalidates your model. You have to retrain your machine learning model, and everything stays in sync. And during the first pass through the training data, you would basically calculate the vocabulary. And then in the second pass, you would basically apply the indices of the vocabulary to the data set. So I think that's a pretty cool way. And that summarizes of like, how do we automate our machine learning pipelines? And with that, we can basically run model updates independently, and we can trigger them by time or by events, and then get a new machine learning model out there. So then the question is like, what do we do with the metadata? And I think it's worthwhile spending a few seconds here on the topic of machine learning model metadata, which I think is pretty important. Folks are always saying, wait, we don't need this. We have already experiment tracking. We use, I don't know, weights and biases, or like whatever tool you want to use. But I think there's a clear distinction here. Experiment tracking is really good for knowledge transfer. Machine learning metadata has a different purpose, and you track other things. In that case, I would say machine learning metadata is basically risk management for your machine learning models. So if you deploy this machine learning model, later down the road, somebody comes to you and asks you questions about the machine learning model. This is your ledger where you would go to figure out like what has happened to this model. What was the initial data set? What transformation steps have been applied? What code was used? What hyperparameters, et cetera, et cetera. So you can basically recompile your machine learning model, so to say. So TensorFlow Extended gives you the great opportunity to use the metadata. It comes with its own metadata library and setup. And the metadata is at the core of TensorFlow Extended. So everything going in and out of those components I was describing earlier is being tracked by the metadata store. You have other options. Weights and biases also now has like an artifact library where you can track similar things. Maybe that works with other frameworks. But if you're in the TensorFlow world, I highly recommend the TensorFlow ML metadata library. And things you can do with the metadata is something like this. First of all, you can track the model lineage. Kubeflow Pipelines even comes with a really nice UI where you can see the lineage. But you can even, if you don't use Kubeflow Pipelines, you can also just query the metadata store to figure out what is the lineage coming out of your metadata store. So here in this case, we can see, okay, in this model was trained with what schema and what transformed examples, and then we can even trace it back to the original raw data set. I think that's extremely important and valuable when we look at the metadata here. Another really wonderful thing we can do with the metadata, through the metadata, we know which model was deployed the last time. We can then go back when we update a machine learning model and say, okay, take the last model, apply a few new examples to a base model, and basically do like fine-tuning to our own machine learning models. And I think this is really a good way of like cutting down the retrain time, that we don't have to retrain from scratch, like that we don't like have to go through the entire data set every time we retrain a machine learning model. I think that's a really cool application coming out of the metadata. And another really interesting application is model cards. And this is something I find really interesting, especially when it comes to communicating your machine learning model with non-data scientists or non-machine learning engineers outside of your team. This could be your project sponsor, your product manager, your project manager. Those cards can communicate what are the limitations, what are the use cases, what are the ethical considerations of your machine learning model, what data sets did you use, what are potential blind spots of that model. So things which should be kept in mind when that model is being applied in production. And you can generate those machine learning models out of the metadata pretty easily from the metadata server. So with this, we basically have checked off most of the boxes, but now I want to show you one last thing, which I think is very important before we deploy our machine learning models. This is how do we test our machine learning models. So testing is really important for us. This goes beyond the small, like the typical split between a test and validation set. At Digits, we make sure that when we deploy a machine learning model, we set aside a test set at the very beginning when we train a machine learning model. We need to make sure that this doesn't sort of like leak into our training process, and we separate this out even long before we start the pipeline. We set this aside, we validate this often internally, and then we run unit tests and integration tests against those test sets. And that means for us, we do a quantitative and a qualitative model analysis. So in some cases, we run it against a larger data set, and we see, okay, how does it do on a broader spectrum? And then in our qualitative data analysis, we run against a very fine-grained set, which is highly curated, but that allows us to really deep dive into every decision the model has made in this smaller data set. The TensorFlow ecosystem has wonderful tools for your model analysis. So I just want to point out TensorFlow MA, which is called TensorFlow's model analysis tool. And then there's also the what if tool, which gives you great flexibility to investigate those models. The later tool, the what if tool, also works really well together with TensorFlow serving, as I will show you in a second. But it basically can connect directly to TensorFlow serving endpoints. And so if you have your machine learning model deployed and you want to test this retroactively, the what if tool is a really good place to start. So I was talking about, like, at Digits, we make those splits between our data set and our test set. That comes out of our ETL processes. They go into basically two different buckets. And we have a process which makes sure that the test set doesn't leak into the data set. In the test set then, or in the data set, that gets then passed to our pipeline. In the pipeline, we split this data set again between a training set and a validation set. So in this case, we would have like 3 test sets. We have training, validation, and the test set. But this is the 21st century, and I think we need a 4th data set. We need a fairness set. And again, this needs to be split way early in the machine learning process, so we don't start to optimize against that. We don't or prevent any leaks against it. And that fairness set can then be used by tools like what if, or by the model analysis tool to figure out, like, are there any concerns in this machine learning model? So after all the machine learning testing, then we can focus on the model deployment. And I just want to give you a brief summary of, like, how do we do this here at Digits. We use TensorFlow serving behind the scenes. We deploy this through Kubernetes, and we have a policy that one pod, one model. So TensorFlow serving gives you the great opportunity to swap out models independently from model deployments. This is great, and it might work for a lot of companies. In our case, we want to tie this to a very specific commit, and that model gets automatically deployed. That whole deployment process is all automated, and nobody has to do anything manual there anymore. As I said, we fix the model versions to Kubernetes deployments. We use mini batching. This is a great feature of TensorFlow serving, which I miss in a lot of other machine learning model deployment frameworks. Since we have a lot of data, we need to get the data processed really quickly. The mini batching is really useful to us. And as I said earlier, it works really well together with the what if tool. If you can't use TensorFlow serving because you have, like, other machine learning models, or you also use other frameworks besides TensorFlow serving, you can always use KF serving, Selden, Onyx, and Bend2ML. There's, like, a large number of frameworks that all do a really good job, I think. If you really want to go for, like, low latency, high throughput, TensorFlow serving is really great. And to give you a quick example of, like, how you could deploy TensorFlow serving, you don't even have to build Docker containers. You can use the pre-built containers from Google, and then you can point that container towards through the arguments towards a cloud path. And if your permissions are set up correctly, you can then read directly from a cloud bucket. Just one thing I would point out, and it didn't fit on that slide, is like when you read from a cloud bucket, make sure that you change the polling time on that folder to something like 60 seconds. Otherwise, you can incur a lot of costs because the standard polling frequency is like 2 seconds at TensorFlow serving. And if you have a lot of models in there and that list call is pretty big, well, at some point at the end of the month, you have to pay on the exported bytes from any S3 or GCP bucket operation. And so that could be expensive. So with this, we were able to basically check off all those 10 boxes we outlined at the beginning of the talk. And just to summarize everything, I think the investment we have done here at Digits pays off because the time from a model idea to a model in production goes from weeks to days. I think that's really great to see here. Also, the tooling makes our workflows consistent. So we use the same tooling and the same workflows for each machine learning model. So that also helps data scientists to like change projects, go from one project to another, because basically they use the same tools, just the business problem is slightly different. So you folks can switch from a computer vision problem to an NLP problem and so on, because the overall tooling is the same. It makes the models comparable and the models reproducible, and therefore also the process repeatable. If you have any questions, find us on Twitter or message me on Twitter or visit us on our website and connect that way. Happy for any questions.
Yes, we got some questions, and hopefully this time you can hear me.
Yeah, I can hear you.
Perfect. Yeah, so we got a few questions. Unfortunately, we're running a bit like late, but I think we will start the next segment a bit like later. So first question is coming from Chris, I guess Holman, and he's asking, hey, can you basically fully automatically decide if the model is like going to production, or you still need to have like a person to give like a final go, right? What is your experience with those things, right? What is the best practices?
Yeah, this is the last step we haven't automated in our pipeline. So the pipeline basically produces a machine learning model candidate. What we call this internally a candidate, and then it gets dropped into a bucket, and we get a notification. We have a Slack channel. Everything we get notified, the team gets notified and it's like, here's the model. It even generates some stats for us, and it shows us like confusion matrices and things like this. And then a human has to look over this again, and then the human elevates this model manually. And then basically the human writes like a little commit, and that triggers a deployment for us. So then from that moment on, everything is automated again. But there's a human in the loop.
Are you planning to open source such a chat ops like for confusion metrics and other things, or is it already like a part of a new TFX add-ons part? So
that's a good question. The chatbot, so the Slack integration itself is already open source.
Yeah.
That is a TensorFlow TFX component. The confusion matrix, that is custom code, and it uses a lot of the infrastructure the way we infer our machine learning models. That might not be generally applicable, but I think it's a good idea to take a look into like how do we pipe this back into Slack? So let me think about this. That's a cool point.
Thank you. Okay, another question is coming from Frank, and he's asking, how much resources does Digit spend to manage Evolve ML Ops environment? I mean, I guess like relatively to the people building the models, right? And building ML infrastructure, basically. What is the distribution of people on one side and the other side?
Yeah. So at this point in time, we spent a lot of time previously to build out the infrastructure, but since we completed that project, it significantly reduced. Like there's almost, I mean, sometimes we have to update like sort of deployment environments if the TensorFlow version changes, or like if there's a security patch coming up for our TensorFlow serving or something like this. But right now we're sort of like in maintenance mode, and that's really great to see. Like we can really focus on the machine learning models, and yeah, that's it was like it took probably like 2-3 months to set everything up. There was a lot of like internal things we wanted to make right. You can be quicker if you have to. So you could probably do this in a couple of weeks. And then I think you can shift back to the model development.
Sounds good. Another question is coming from Hubert, and he's asking, how would you no. How would you tell TFX works with image data? I found that most of the components work well with tabular data, but there are like few resources about how to approach image data.
Yeah, that's true. But I would highly recommend check out the book we wrote about TFX. There is a custom component in there where we ingest data for a computer vision problem. And we wrote in a custom data ingestion component for images. We use for our NLP problems standard components. That works also really well. So TFX has greatly evolved over the last 12 months. I think it's a real powerhouse now to use that in the context of pipelines.
Is there like any active developments in that direction? I don't know. Can people contribute and like help with such custom components, or like what is the current setup from TFX side?
Yeah, so the TFX has a special interest group called TFX add-ons, where external folks can contribute component ideas and implemented components as well. And hopefully that turns into sort of like a little exchange place where folks can exchange components which work for them. We will, in the next couple of weeks, take a look at those, like open sourcing those image components for the data ingestion. There's other components for like generating those model cards automatically. There's a variety of ideas what we would like to contribute to this, but like check out the TFX add-ons SIG group.
Yeah, sounds good. Another question. Where is in your process would you include the monitoring of a potential model drift? Is it a part of easy deployment?
It actually happens afterwards, or basically it happens at the beginning of the pipeline. You take a look at the data set, and we take in TFX, you can read spans of data, and you can compare them then against the last snapshots of your data set. And with TensorFlow data validation, you can compare the snapshots, and it allows you to compare the data validation. So for example, if an entire like column is gone, or maybe you have like new labels coming up, or a label distribution is changing, that is something you would detect in your data validation step.
Cool, awesome. Thank you for presenting all this like amazing overview of TFX and giving good ideas how people can introduce it to their own production pipelines.
Yeah, thank you. Thanks for having me.
Thank you. Have a good one. Okay, so now we actually running like 5 minutes late, but we're gonna have like a short break, and after we're gonna continue with the lightning talks. So grab some water and see you in 5 minutes.
Hello, guys. Welcome back. I'd like to introduce our next speaker, who is Hubert Brilkowski. Hubert is a machine learning engineer at Brainly, and he's going to tell us about deploying production-grade models at Android devices. Hubert, it's all yours.
Okay, thanks. So first, I might say that I'm really happy to be here among such great speakers. And today, I want to talk to you about the bumpy road to production-grade models on Android devices. So we have only 15 minutes, so it will be pretty short route, but let's get started. So what does it mean even that the model is production-grade? I think there are a few components here. So first, it performs well enough in the metric we've chosen, like accuracy, precision, recall, and satisfy other metrics like inference time, its size. But also, we should know exactly on which data it was trained, and we can fairly easily train it to achieve the same performance. So to simply put it, it's reproducible. And how to achieve it? So our road starts with an idea, goes to translation to machine learning problem, then we gather data, then we iterate on the model, deploy it, and finally observe the metrics. So some of the steps might be iterational, like the iterating on the model will go right and back. And as it was said earlier, the data will change over time and we get new ones, so why not use them to retrain the model? But first, let's start with the idea. And the example I will share was a real feature from the product. So one of the features of Brainy app is that the users take a photo and we can search via those photos. And some of these photos this user took were not of that good quality. So were out of focus, were too dark, or had motion blur or flare. And we were wasting computing power because, well, it was impossible to find the answers for that queries. And the users were unhappy because they had to send the image to our backend, wait for some time, and finally get the feedback about this. So both of sides weren't happy about this, so why not fix that? So our goal here was to detect these bad quality images and hopefully immediately on device to tell the users that, hey, something wrong is with your photo, can you please retake it? And we get this idea from the business, but now we want to translate it to the machine learning problem. And this is fairly important because it will start our research, enable us to look for open source data set, and maybe even find some pre-trained models, for example, on TFUG. And here in this case, it was fairly straightforward. It's in binary image classification. But even here, I think we should stop for a second and wonder which of these two classes we will predict. Because if we are making a detector for bad images, like here, we will probably measure precision and recall. And which class we choose as positive example will further influence how easy it will be to interpret the results of how our model scores. So here, probably the good idea would be, since we are making the bad images detector, to stick with marking the bad images as ones. And it's not always this straightforward, and sometimes it will even take some research or even creating the proof of concept models if given idea is even solvable using the machine learning. And here, this problem was chosen because, well, we assumed it is solvable, and, well, it was. But also, it's very easy, and we could even test the deployment on the mobile devices, which is a long run. So then, when we have our classification, how we gather data. We know that about 5% of the images submitted by users are of this bot quality, like we stated. But if we send just random sample from the database, from the historic data that we have to the labeling, then well, we would end up with really imbalanced data set. So here, for example, we can use some non-machine learning metrics like Laplacian variance, like variance of Laplacian, like brightness, histogram, looking at image histogram to find more or less balanced data set and then send that to labeling. Here it was even easier because we had historical data. So we chose half of the images that we know that OCR found some texture, and half of the images that we know that there was no texture. But it could be for some other reason. Like there was an image only on the photo, or like somebody took a picture of their living room, and they could be of good quality. But this is only the initial split, and then we need to send this data to labeling to find which of our images are actually good and which are bad. And here is this is fairly important question we should ask, like how to frame the problem for the human labelers. And if we have in-house people who are labeling, it's a little bit easier, I think, because we could talk to them, we could ask them, and if they have problems, we are in quicker feedback loop and we can talk about it. Of course, it's a good idea to label at least some portion of the images by ourselves, so we'll get insight of the data and see how complex task is. But if we want to use the external workforce like the SageMaker Ground Truth provides, for example, which is amazingly easy to use, we must understand that the people who are doing this labeling are dealing with a lot of different tasks, I assume, every day. So the easier we frame the problem and the less confusion that there might be about their task, the better results we'll get. So if we were to ask them, is this image of good quality? Like personally, if I saw this problem frame, I would wonder, what does it even mean? Like, what is a good quality? Like, is this picture good enough to win some prize, or is it like that I can see something in this picture? So this was definitely not a good idea to send this task to labeling, but instead we went with sending them, I think, fairly simple task. Can you read the text on this image easily? And I know it might be framed even better, but I think if you were to just drop in instantly with this question and have shown these two pictures, of course, there were examples for what bad and for both of the classes, I think it is fairly straightforward. And the results were actually satisfying. So I think the question stated for the freelancers was at least good enough. So now we can start iterating on the model. So as it was stated in previous presentations, so I might repeat a little here, we can start in notebooks because, well, it's fairly easy. We can get some initial results. But I assume that at some point we'll want to move to a more repeatable environment. And here, like TensorFlow Extend is a great example of that, because we can replay our whole pipeline. We can see what went wrong. We can get the insights about our models. So big plus of TensorFlow Extended is that pipelines constructed there will always have all needed steps executed that you programmed. So it doesn't matter if you think that your data split is equal. It still will be checked in the data statistics component. And believe me, it helps. Like one time I made a mistake and I overwritten my data set. I left some ETL task running and it overwrote my data. And I haven't noticed that. My model was simply not training and it was gaining totally garbage results. And I was wondering why. I checked the lineage and I saw in the statistics component that all of my examples were of single class. So I had only bad images in my pipeline, so no wonder that, well, there wasn't training anything. And I assume that if I were to train the same model in the notebook, it would take me much, much longer time. And I think also a great thing here is that the evaluator component actually executes evaluation on your final model converted to TF Lite. So I knew that my model was evaluated, the model that was evaluated was the same one that the users will face. And there's also a fairness tool built in, which in this case might help us to see, for example, if we are not labeling some kind of devices, for example, low-end devices, as always creating bad photos. So this also is, I think, because it's so easy to plug it in, it's higher probability that users, data scientists or machine learning engineers will use that feature. So the next thing is when we finally have the model that we are satisfied with, we can deploy it. And here, when we are deploying to the TF Lite, we need to convert that model, and it can be done as a step in the pipeline. Hard thing here is that not all of the TensorFlow extended preprocessing operations can be included in TF Lite model. Basically, they are not implemented in TF Lite libraries. Not all operations are. For example, I had troubles with scaling and transforming JPEGs from any size. Like when I had the set size, I want to rescale from 512 to 256, it went fine. But thanks to using TFX, I realized that on the initial stage of the project. So when we want to deploy, we can include this in our Android application using the TF library, but TF Lite libraries. But we can also use Firebase. And here, I think it's a great tool. And to be honest, I do not know of any alternatives. It enables Android developer to write an app in such a way that the model will be downloaded after installing the app. So the app itself will be smaller, and it makes user experience better. Models can be updated without updating the app. The models can be A/B tested. And under tooling that is already in Firebase, it makes it possible to create the kill switch if we find out that our model has a critical flaw. So, for example, if our model would for some reason learn that if there's a seam on a page, it will always detect the bot quality because we had such data in our training, we can turn it off and turn it on again after we will have better model, not so biased. So now that we deployed it, we want to probably observe metrics, whether it actually helps our users or not. So here we have Firebase, but we also need some basic statistics and, well, logic. So although we can pull the metrics and the results of the A/B tests and go from the Firebase, it won't make all of our job for us. We still need to think if these results make sense. For example, in that case, we might want to optimize the time from the user that make the photo to the first result they get. So here in that, maybe even the first results they got that they were satisfied with. And if we measure that and it actually gets shorter, we can assume that probably our model is good. But if it's increased, or even the users that got the feedback about retaking the photo or uninstalling the app, then maybe, well, model itself is good because it has high accuracy or high precision, but still it's not putting a business in a good place. So I think it might be a good idea to reevaluate, maybe not the model, but how it used. Like instead of checking the picture afterwards, when the user clicks the shutter button, take 5 photos and choose the best one using this model. So some of the resources that I can recommend, well, the TFX documentation is a good start. And the book, I read it heavily during my development, and I deployed the kubeflow pipelines on AWS and TFX there, and it was real painful. I had to read a lot of source code to understand what is going on there. But still, the book was much more resourceful than TFX documentation. And I also included links like a TF Lite tutorial on GANs, which might be interesting, and the repository that contains a lot of resources about the TensorFlow tutorials and examples. And also, in the end, there's an ML canvas This is a tool that helps you define some of the things that you will need to go through, and we used it in the most recent project. And I think it helps to ask those questions that you probably will still do, but it helps you frame it a little better. And at the beginning of the project, you'll have a lot of stuff formalized when you look at this, well, piece of paper. So thank you. That's all.
Thank you also for your time. It was an amazing presentation, and I think people definitely did learn quite a bit with that. Unfortunately, we didn't have like a lot of time, so we are going to share a link to Brainly, and also your Twitter should be like available. So please follow Hubert. He has like amazing ideas. Thank you for your time.
Thank you.
Okay, so it's pretty exciting that we not only talking about bringing the model like somewhere, but actually like about production lifecycle. And it's actually interesting that by the end of this day, right? Because I mean it's kind of almost a day by 3 hours already. We started with Hannes, right? And now Hubert added like a bit more, and now we're gonna add another speaker who's gonna be talking like a bit more structurally about those things, right? And bringing some open source solutions that might be making it even more convenient, right? So please welcome Hamza from TinyML. He's actually based out of Munich with his startup. So looking forward to hear what you're going to tell us.
Cool. Thank you, Sergei. I hope everyone can hear me. And thanks for the invitation. It was a great event so far. And indeed, I'm going to be providing a bit of structure to what has already been talked about before, especially by Hannes. That was a great talk. Just a bit about myself. My name is Hamza. As Sergei said, I'm one of the co-founders of an open source MLOps frameworks based in Munich, Germany. TensorFlow is the name of the framework, if you want to check it out. Originally from Pakistan. I've been solving MLOps problems now for a few years, working in the industry, specifically working a lot on use cases like predictive maintenance. That was really where I faced the most problems. And this is also where our company is coming from, where we were basically solving MLOps challenges. I think we were also one of the early adopters of TFX, like really 0.13 or something. I got the chance to meet the TFX team as well. So it's amazing to see a lot of familiar faces also here today. So this talk actually is about, like again, something that you might have heard about like a lot today, production ready in machine learning. Or the 12 factors for reproducible machine learning. Now, if you were wondering where the name is coming from, it's inspired by the 12-factor app, which is something that especially software engineers who are listening might be familiar with. It's something that was created by, I believe, the developers of Heroku in 2011, basically as a set of golden practices to solve for the portability and resilience of a web application. So not a machine learning application, but a traditional web application. And like a checklist to go through if you wanted to see if your application was production ready or not. And when we were doing MLOps at our company, we figured out that there was no such thing really for machine learning. And there were ops people in our team who really didn't enjoy that there was Jupyter notebooks and scripts all over the place, which essentially, were run ad hoc. And of course, the ML people were not super happy when the ops people were saying, yeah, you need like reproducibility, mutability, and all these concepts they didn't really care about. They just wanted to experiment. So we came up with, basically we sat down together. We came up with some rules or some best practices, which we then refactored, ironically, into the 12-factor that I'm going to show you today. It's basically a repurposing of the original 12 factors as a checklist of things that you want to go through if you want to make sure that your machine learning application is production ready or not, and specifically whether it is reproducible or not, which is, as we heard from Hannes as well, and Hubert as well, that which is one of the critical pillars of ML in production. So going quickly through, let's talk about the factors. So this is, like as I said, a checklist. So I'll just talk about the factors. It's based on a longer blog post that you can read, which I'll link to at the end. And the first thing that we have to talk about is versioning. It's something that a lot of software engineers, who are code developers or from conventional backgrounds, understand a lot. But in machine learning, it's unfortunately not really adopted so deeply as it is in conventional software engineering. It's also doubly complicated because it's not just about code, it's also about the data in machine learning. So you need to version both. And versioning, I don't mean versioning just in terms of having a commit every now and then. It basically also means to have a notion, a semantic notion of what that commit is, so that you can come back to it and understand what's happening. And you need to make some sort of link between what's happening in the code and what's happening to the data. So there's a really deep connection there, which I think Hannes also talked about with metadata management. That's a possible solution to this. But you need to have a version application if you're going to do production machine learning and you want to reproduce your models. The second is explicit feature dependencies. I'm a big fan of this analogy that one feature in your machine learning model is like a pip package in your code. So if you fix pandas 0.25 and they go to 1.0 and you haven't fixed it or pinned it, then you're going to break upstream, downstream, a lot of things. It's very similar to features in data. I know there are feature stores now. People talk about Tecton or Feast or Hopsworks, which is also great to solve these. So you want to make your features that go into your system as explicit as possible, as descriptive as possible. And feature stores are a great way to do that. Another way to do that is what we also saw, model cards, where you can basically see the list of cards and see, okay, what the model basically is getting at as input and how it's being calculated, which is super important if you want to reproduce it. Cool. Next, descriptive training and preprocessing. Writing readable code is actually very important. Following PEP 8, making the variables mean something, just doing proper software engineering, good quality code with reviews is very important. Especially important with training and preprocessing. It's written a lot nowadays in throwaway scripts in Jupyter Notebooks, which is a bit hard to reproduce. But you want to be able to do that from the start and enforce that from the start in your team. You also want to be separating code from configuration. So you don't want to be doing things like, okay, this is my split, it's hard-coded in the code, or these are my features, or my label, or my loss metric. You want to separate that from your code and insert them at basically runtime. So, and essentially track as these things evolve, because these are going to be important when you go back and look at your trainings and understand what's happening. Number 4, testing, no-brainer, right? I think Hannes talked about it a bit as well. You need to test your code. We all know unit tests, integration tests, smoke tests. Those are important. But you also want to be testing your models, and you want to be testing your data. So it really means a bit like different things, and there's lots of tools out there that help you do that now. I think Great Expectations, for example, is a good one for data, or TFMA. Testing your data, basically unit testing on a feature level, and writing integration tests for your transform code, for example, that on a static bunch of data is producing the right transform all the time when you make changes. These things are super critical in production, and people should pay attention to them even at the POC level. Reproducibility of the trainings themselves are very critical. For this, I would recommend to use pipelines. I think we talked a lot about TFX today. I've been using TFX for more than a year now, maybe 2. It's a great tool. There's also other options available, of course. Whatever you go with, I would suggest try to automate as much as possible. And it's very essential that you get that as close to training day 0 as possible, so that you're able to go back in history and reproduce training results even from the beginning, because you'll be surprised that as things evolve in your organization, how critical it is, stuff like security or people leaving or just not being able to reproduce a model will have a huge impact on the bottom line at the end of the day. So that's very critical to enforce at the start. Continuous trainings. I heard a question asked about how do you do continuous trainings, when do you trigger it? Model drift is definitely a problem which lends itself to continuous training. What this factor basically means is that you should have a setup available for continuous training from the start. So you should think about that, because a lot of machine learning models lend themselves to model drift, concept drift, or data drift, whatever you want to call it. There's some amazing tools like Arise AI or Evidently out there, which actually spot those for you. Also TFTV, TensorFlow Data Validation, helps. You want to be able to run it in a way that you're able to consume new data and not only train a new model, but also validate that what happened previously hasn't been changed in a way that you don't understand. So something like the ChatOps solution that Hannes proposed is great, that you produce metrics. You want to be able to keep a track of all of that, and you want to be able to automate that so humans don't really or get minimally involved in this process. It's super hard to fully automate it, but trust me, the effort would be worth it. And actually, it's essential in reproducible machine learning. Tracking results, again, experiment tracking is very big. Weights and biases, I think one of the winners there. Tracking results in an automated fashion, especially, is very cool with like weights and biases and other tools. You want to include that from the start. You don't want to be using CSV files or Excels and sharing them around. Honestly, it's not really scalable and it doesn't really work. Don't try it, even if you have a fancy spreadsheet. Just use tools that track it automatically, your metrics, your losses, what's happening in experiments, in your notes. These things will pay off. Right. Next thing to understand is experimentation versus production. Notebooks are very hard to productionalize, and they are very good for experimentation. Pipelines are very hard to develop, maybe, but lend themselves to production. There's a balancing act. Nowadays, I'm promoting to start building pipelines from day zero. This is also what we're doing with ZenML. We're trying to make it flexible enough that you're building pipelines in a way that it doesn't feel too much of an overhead to build them, but you're also, so you can iterate quickly, but you're also really just building proper pipelining tools that can scale. So from training day zero, if you can build pipelines, it's amazing. Obviously, there's a caveat. You want to explore the data in a Jupyter notebook and generate some statistics, sure, but try to minimize the throwaway code as much as possible. This is going to be critical to like when you shift to production, because then you're not going to have to transition and escalate the code from a scripty POC sort of setting to a production setting. That's going to be a big headache. So the less code you write in that phase, the better. So yeah, that's always a balancing act. Very similar, there is going to be a data parity between training and serving. Training time, you're making some assumptions, and if the environments of training and serving are different, then you're gonna have you shouldn't be surprised if your models tank in production. It happened to us a few times, because you're basically, I mean, like a trivial example would be if you're pre-processing and normalizing the data in training time, but you don't do that in serving time, you're gonna be exposing it to raw data, which is gonna just blow up, right? It's not gonna, the model is not used to that data. So embedding the pre-processing graph would be an idea here, there, like for example, TFX does. Correctly embedding pre-processing towards serving can also be achieved through serverless functions. You just need to be able to understand up and downstream like data dependencies. And the best way to do that organizationally at a cultural level is to move the serving as close to the training environment as possible and ensure that the people who are training are also serving. This is really the bottom line of a cultural shift that can happen with MLOps, as it happened in DevOps, that if you train it, you're going to run it and you're going to deploy it. And if the data scientists are given the tools to do that from the start, they can also test the serving environment while they're training, which is really the golden line that you want to draw. Nice. Moving on, comparability is very important. I think Hannes mentioned that it was hard for them to have comparability or at least to solve that. It's a problem for us as well. So if a model is being built to solve a particular task, you want to be able to compare all the models that have ever been created in a simple manner at a metrics level or so on and so forth. This is very important to ensure that there's a mechanism in place that the evaluations are tracked centrally and can be compared very quickly. You can even do that at a pipeline level. So like, for example, ZenML helps with that. 11th factor, performance and monitoring. Monitoring is a very big topic. It boils down to really ownership. So the data scientist should have ownership of the monitoring up till that level, I would think. Again, if you train it, you run it. There's many ways to monitor models, whether you monitor the input distribution, the output distribution. There's different ways to detect at a feature level the skew or the prediction level the skew. Lots of different tools out there for that. Anyway, you need to solve that if you want to really have production-ready environment, because you can't really deploy a model without monitoring it because of the dynamic nature of data that happens and the hidden nature of faults that can happen. Machine learning models do not tend to fail hard. They tend to fail silently hard. That's the problem. So you need to be on top of it. Every model needs to be deployable. That's the 12th factor. Every artifact that you produce from a training should be deployable at the end, meaning not just a copy paste of a file. Means also the code, the assumptions that you made, the data that you trained on, the pre-processing, the splitting, all that. That should be packaged together and should produce a deployable machine learning model at the end. If you don't produce that, then it's not reproducible and it's not really production ready. That's something that we enforced with all our developers who joined the team, that they really ensure that that works with the ecosystem. Again, the best is to shift the deployment ecosystem as close to the training ecosystem as possible, and so we minimize all those risks. Cool. So that was the lightning version of this talk. It's based obviously on a fuller or like a longer blog post, which you can find here. I tried to copy the short URL thing that Peter showed in the morning or a few hours ago, but there's also the full link if that doesn't work. Please give it a read. We also have some other articles there which you might find interesting. And if you want to see all of these things in action, again, I'll just take a few seconds to talk about ZenML, which is the MLOps framework that we're developing. And it's essentially looks like this. So I don't want to plug it or spend too much time on it, just giving you an idea of how it lets you create a pipeline in a very simple mechanism, like sourcing from a data source. It versions that data source. You can add steps in the middle, like a tokenizer. And for NLP, you can add a split, like a random split, and add a trainer. These things are obviously modules in Python code that are then pinned at a Git level, at a Git SHA level. You can run it locally. You can run it on the cloud. You just need to fix that line. You can get all the historical pipelines. You can view the schema of a pipeline, view the statistics. You can compare pipelines. There's a lot of things built in. The goal of ZenML is really to be a simple, intuitive interface to these 12 factors, and also to give you a head start in production machine learning. And if that's anything that interests you, if you think that a simple interface is what is necessary right now and is missing in the MLOps landscape, then please go over to our repository, give us a star if you want, check it out, pip install it, it's just a package. Try out our pipelines and communicate with us via Slack or on the GitHub issue board. Super looking forward to this journey. And again, thank you everyone for the invite, and hope you have a great evening.
Thank you for joining us. It was an amazing presentation. So definitely good luck with your open source solution. Looking forward to see you hitting like 10,000 stars at least.
Cheers.
Have a good evening. Take care. And we're going to share the links also to your products.
Cheers, Sergei. Bye.
Cool. So now we're going to add all of amazing speakers, organizers. Sorry, not speakers. Speakers already like went doing their business. Now it's only organizers. So let me see if Sashko is also here. So how's it going, people? Like, are you happy with the results?
Yeah, it was amazing.
Yeah, I think we have almost spent 4 hours, and it just flew away time. I think there was really interesting topics, and lot to learn, many open source repo to look into to even learn more. So yeah.
Yeah, it's totally crazy because you mentioned like 4 hours, right? Currently, I'm using like a standing desk, right? And I didn't notice that I was like standing all of this time, more or less, right? So it's been already like 4 hours. If content is amazing, right, you just like enjoy it, right? So I hope our community also did. I mean, our 3 different communities from 3 different countries and cities did enjoy it like a lot as well.
Yeah, definitely.
Cool. But in the beginning, we said it's going to be a surprise, right? Does anybody still remember what was the surprise or the promise?
Let's see what the chat says. Nope, nobody remembers. So
They already forgot it. There was a books. So how is it going to work? Like, can you guys like remind what was the deal?
yeah, so we said at the beginning that those people that came up with questions for each one of the session would participate in the possibility to win some books. So we pseudo randomly, I would assume we would choose the winners for each one of the session. I would say it was based on the question, and if we brought them up to the speakers, they rated a high probability. And as we had 5 books for each session, we also made some fill-in where it made sense.
Yeah, so it's almost just like a drum roll thing. You already announced like a first 5 winners.
Yeah. Yes.
Second one about machine learning design patterns, right? So this is like one of the books that I actually haven't seen yet, because like one from Hannes and one from Pete I had before, but design patterns maybe not yet.
Yeah, I added that book. It's written by Lack, Sarah, and Michael.
Nice.
To be honest, I don't know Michael, but Sarah and Lack is very active in the Google Cloud DevRel TensorFlow community, and I've been writing a lot of good stuff. So I look forward to it. I haven't read it yet, but I have seen really good recommendation about it.
Yeah, good system design, right? And the last. Yeah, and we see the names, and in some cases you can kind of like see that the names are repeating, right? But it's also because like a person or people were asking like really good questions, right? So we decided that it's like a good opportunity for them to share it. I don't know, either read the book, right, or to share with the community. So I hope you're excited with your new books. And how does it work? How do they get the books? Like, what is the setup?
So how do you claim the book? So the 15 people or the 15 names, there are some duplicates here, but send me an email to the email address listed here on the slide up in the right corner, amontene@google.com, with your details. So ideally your YouTube name, and then your full name plus an address, and I would ensure to ship it to you. Okay, so I hope that all of the winners are listening to this and figure out that they have to send me an email to get their book.
Yeah, maybe if you know the winner, just like ping this person afterwards and be like, hey, you actually won a new book, right? So they're not going to get lost, basically. Yeah.
Also, I'm assuming this event will be on YouTube for a while. So if anybody go and see it later on, the finals, they will also realize it.
Yeah. I don't know how does it work with GDPR, right? We're not going to save the names like anywhere else, right? And the data stored like on the YouTube server. I'm kidding. Like, this is not a real concern.
Okay. Good to hear.
At least not for us, right? We're going to delete all the data pretty immediately. So maybe last words from our side.
No, I'm just happy that I feel this was a success. We had amazing speakers. I really feel we had a great lineup. We had a good participation with the community asking questions. So super glad to see so many interested in the topics. And if you are from Copenhagen, feel free, of course, to join the community or meetup. Send also your suggestion of future events that we could do.
If you are traveling a lot or you are planning to travel a lot after the COVID times, if they ever end, feel free to join on all the 3 meetup groups. Why not? It's lots of fun.
Also.
It's a good opportunity, right, to actually meet all of those talking heads on YouTube in actual real life setting, right, and maybe get some, I don't know, beers or what would be allowed at that time, right? Yeah, and if you would like to watch those videos later, as Alejandro already mentioned, they're gonna stay a stream on YouTube, and maybe at some point we're also gonna, split them into like smaller chunks and like label it, right? But it might take a bit of time. There was also a question about PDFs of the presentations. I guess we're gonna ask the speakers, right, and try to share those ones, at least like via the meetup, right? So it's also a good opportunity for you to subscribe, right, and get updates about the next events. Yeah, thank you everybody joining, speakers, like you organizers, right, and the audience, right, because without you it wouldn't be possible. So it was definitely a blast for me.
Yeah, thank you all.
Thank you. Have a good day and a good week.
And a good evening. Let me just move my cursor.
Bye-bye.
Bye-bye. Take care.